Hello my dear students, I welcome you back to PW JEE English channel, and today on our one shots of chemistry we are going to start with the big daddy, the big boss, the most important chapter of chemistry, that is chemical bonding. Because in organic chemistry you just see the question, tick the answer, move ahead, will give you marks also, will save your time also. So because of the huge importance of chemical bonding in whole of the chemistry, I have personally divided these chapter into two halves. One in this short and the other short will be of chemical bonding again, the chemical bonding 2, because it is our moral right that we should provide a platter which will serve all the logics in the simplest way. Do not worry about writing those lecture notes because you can obviously download all of them for free with the related DPPs and assignments from our PW app. The link to which is given in the description section, because PW is the most loved organization trusted by millions of students every year. So let us dive and explore this side of inorganic chemistry.
So to begin with, a chemical bond is basically a force of attraction which holds all the constituent atoms of a molecule together. Now we very well know this, that atoms in nature exist in form of molecule except elements of inert gases. Group 18 elements are known to exist in nature largely as monatomic molecules. So people at initial point of time, when quantum theory was not known to the scientific community, they thought that inert gases must be having some characteristic because of which they are existing freely stable in nature. But all molecules, in order to acquire and become just like those inert gases, will chemically, as an electronic transaction will take place so that their electronic configuration can become as that of the closest inert gas. So these chemical bonds are nothing but the ability of those atoms to attain that inert electronic configuration. Now, because now, since we know through atomic structure that atoms combine in order to pair their unpaired electrons, which can very clearly be seen by the approach of these two hydrogen atoms. When these two hydrogen atoms approach each other, if they are far apart, the distance between them is large enough, the potential energy is zero. But if they approach each other with their electrons in parallel spin, then they are not able to form the bond. But when these two hydrogen atoms approach each other with opposite spin at a distance of about 74 picometer, the closest distance of approach. Why? Because when two atoms approach closer to each other, there are repulsive forces also. Repulsive forces over here I have represented with the red lines. The repulsive forces between nucleus, the repulsive forces between electrons. But obviously, with opposite spin, when they are approaching each other, there must be some new attractive forces. The new attractive forces, which NCERT also beautifully signifies as the new attractive forces represented by this thick line, the nucleus of first hydrogen and the electron of second hydrogen, the nucleus of second hydrogen and the electron of first hydrogen. These attractive forces must definitely be larger in magnitude. That's why these attractive forces are holding these two atomic molecules, that these two atomic species together to form a molecule. And how thermodynamically it is seen that they like to be closer to each other, because when they approach to each other with opposite spin, they reach a minimum energy termed as their bond energy or bond enthalpy. So whenever atoms approach each other, energy is always released when they form a chemical bond. This we now know because we know atomic structure through the quantum side of it. But initially, at that point of time, Kossel, Lewis, and Langmuir, what they assumed was atoms approach each other in order to attain electronic configuration that is closest to that of their inert gas, and hence the word came octet. If you just go to helium, doublet can also be achieved by hydrogen and lithium, because helium is closest to hydrogen and lithium. But for other species, generally it was said that atoms combine with each other to complete their octet. Although through quantum theory we know atoms combine with each other to pair their unpaired electrons, and in order to pair their unpaired electrons, obviously orbital overlap will take place. I'm I'm sharing this valence bond theory, VBT logic of chemical bond formation initially only because we want to know the logic and do the relevant question asked by JEE. So this is the NCRT beautiful graph which tells you that when atoms approach each other, which to the closest distance of approach for a chemical, for a covalent molecule, it is called the bond length. So what will be the bond length between when electrons are shared with opposite spin? So the distance between the nucleus will be termed as the bond length. So bond length for hydrogen will come out to be 74 picometers. And why it is forming a bond? Because it is attaining the lowest possible energy. So if you supply this amount of energy, what is it? 435.8 kilojoule of energy. If 1 mole of hydrogen is supplied with this energy, obviously they'll fall apart. They will spread apart. So whenever a chemical bond is formed, energy is always released. So basically, why a chemical bond is formed between any species? Because they acquire a noble gas configuration. Initially, this was the story, the octet rule. When they approach each other, why we say that attractive forces dominate the repulsive forces? Because through thermodynamics we see that the energy is getting reduced. So if energy decreases, stability increases. So if energy decreases, stability increases. And obviously if I'm stable, then I'll not react, so I'll be not reactive, or I'll be relatively stable. Now, so what type of chemical bonds were proposed by Kossel, Lewis, Langmuir? The initial bonds that were known to the scientific society was the strong bonds. Why I'm to the chemical bond, that is the attractive forces, why I'm naming as strong and weak? Because of thermodynamically speaking, if I am forming a bond that is strong, then I will be releasing more amount of energy because I'll be feeling more happy. So approximately energy of somewhere around, not exactly, but somewhere around 200 kilojoule is released when a strong bond is formed. And when a weaker bond is formed, the value lies somewhere between 4 to 20 kilojoule of energy per mole. Now, sir, what are these weak bonds? They are when the physical forces of attraction that exist between molecules, we will discuss them separately, the hydrogen bonds and the van der Waals forces, the intermolecular forces of attraction. But presently, initially, we'll talk about the strong bonds, the ionic bond, the covalent bond. Obviously, by transfer we form an ionic bond, by sharing we form covalent bond. When one atom donates electron to another atom, forms a coordinate or a dative bond. And metallic bond is basically the covalent bond formed by the metallic atoms, those atoms who exist in nature as metals. The covalent bond formed by those metals are termed as metallic bonds. This is a basic, although in the modern physics side of it, you'll definitely say that metallic bond is actually a attractive forces between the sea of electrons and the positive ions present in that metal. To that positive ions, theoretically, they are also termed as vibrating kernels. But these are all theoretical things which you will be dealing in the modern physics side of the physics more. So for our chemistry, whenever atoms exist in nature in form of a solid metal, then the similar covalent bonds, to us we will simple refer those covalent bonds as the metallic bonds formed by their valence electrons. So discussing more about the octet rule and the ionic and covalent bonds. So how ionic bond is formed? Very easy, we know through class 9th basics. Transfer of electron, the basic example, sodium has an electronic configuration with valence shell configuration of 3s1. Chlorine has an electronic configuration, valence shell electronic configuration of 3s2, 3p5. If sodium donates this electron, loses this electron, forms a cation, sodium cation, reach a complete octet, just like that of the closest inert gas, neon. Chlorine accepts that electron, completes its octet, becomes just like that of neon, the complete octet, and therefore the attraction force between Na plus and Cl minus is termed as the ionic bond formed between them. But remember, what is actually the bond between them? The transfer of electron. Although after transfer of electron, a cation and an anion is formed, and obviously a cation and anion will attract each other through the electrostatic force of attraction, and therefore ionic compound generally exist as a solid, because the attraction force between cation and anion is a strong Coulombic force of attraction. Now, if I wish to be attain a stable inert configuration, I can even do that octet. I can even attain a stable octet by sharing. For example, fluorine and fluorine sharing this one electron. So bond order of this F2 molecule will be 1. So what is bond order? When a covalent bond is formed, number of shared electron pair is termed as bond order. So to fluorine, what we will say, it has got whatever my valence electrons are. Now, after formation of a covalent bond, they are represented as lone pair electrons and bond pair electrons. So if somebody asks you how many lone pair of electrons are present in F2 molecule, so total lone pair electrons will be 1, 2, 3, 4, 5, 6. So there will be 6 lone pair electrons in the molecule. And how many bond pair electrons? One pair of electron. Bond pair, as in we are counting pair as 1. Now, obviously, hydrogen exists as H2 and attains a stable configuration like helium. So, doublet and octet. So, molecules exist in nature, atoms exist in nature as molecule. Initially, it was proposed that they do so in order to complete their octet. And by completing their octet, what they attain is a stable electronic configuration. Therefore, give rise to ionic compounds and covalent compounds. So let us quickly go to some properties of ionic and covalent compounds. Obviously, ionic compounds have attraction forces for example, you have a sodium cation. Sodium cation will attract chlorine anions from all direction, because a positive charge will attract negative charge from all direction. So ionic forces or electrovalent ionic bond or electrovalent bond is that type of force of attraction which is non-directional. While if a fluorine is attracting another fluorine atom, forming a F2 molecule by sharing, or hydrogen is forming a covalent bond with another hydrogen sharing, then this sharing, this attraction force, this bond order formation will be specifically directed to that species only. So this is a very important point, that covalent bonds are termed as they are directional in nature, while electrovalent or ionic bonds are termed as they are non-directional. Discussing more about ionic compounds. Whenever an ionic compound is formed, somebody is losing electron, oxidizing. Somebody is gaining electron, reducing. So it's a redox reaction. And obviously, whenever a bond is formed, energy is released. So when energy is released, process is termed as exothermic. Next point, ionic compounds. As I've told you, after the transfer of electron, cations and anions are formed. So what is the attraction force between them? Sir, strong Coulombic forces of attraction. So strong Coulombic forces of attraction generally brings those ionic compound into a solid crystal shape, and solid crystal is supposed to have a strong formation of lattice enthalpy. The amount of energy released when a ionic compound is formed is generally high. So in order to bring them far from each other, the melting and boiling point will be higher. So ionic crystals have high melting and boiling point. Now, because they form a solid, so these solids are hard but brittle, because these arrangement of plus minus plus minus plus minus sometimes may arise, then minus can be next to a minus. So they are hard because of Coulombic forces of attraction, but because there is an array, there is an arrangement of n number of cations and anions, so some occurrence may also be there when minus can be approached by a minus. So they are hard also, but they are brittle also. Now, because they have constituent ions in their composition, so obviously the rule of solubility is like dissolves like. So who is the universal solvent? Water has got high dielectric constant. So water or any polar solvent can easily dissolve these ionic compounds. Ionic solids they only have empirical formula. There is no such term called molecular formula, because whatever formula of ionic compound you have, I already told you, they form an array. So for example, you have a solid, you cut out a unit cell, and in that unit cell there may be presence of so many sodium cations and so many chlorine anions, but the molecular formula that we get is the simplest formula. So for ionic compounds, existence of only empirical formula is known to us. There is no, because they are obviously an array, so there will be n number of both cations and anions both, but the simplest ratio for ionic compounds, that is the empirical formula, becomes their molecular formula also. So molecular formula essentially per se is not valid for ionic compounds. Now, because ionic compounds have ions, by the name you can see, but in solid state that those ions are attracted from each other. So in solid state they are not conductors, they are insulators. But yes, if you melt them, so in molten or fused state the ions are free to move, so they'll conduct, and obviously when they are dissolved in water they make the water conducting. Talking about the covalent bond, as I've already told you, it is directional in nature. Remember this point. A covalent bond may be polar, may be non-polar. Electronegativity in periodic table we have done. If a bond is formed between two atoms of equal electronegativity, so the covalent bond will be non-polar, and if it is formed with unequal electronegative atoms, it will be generally polar. Although we'll talk about the dipole moment, where we can see if different electronegativity atoms also forms a molecule, then the vector addition sometimes make them non-polar. We'll see them after VSEPR theory. Now, if two atoms are sharing electron, the number of shared pair is called bond order. So if bond order increases, two atoms approach each other much closer, so bond length decreases. And if two atoms are bonded by more number of bond pair electrons, then obviously it is difficult to separate them, so bond energy will be high. So bond order is directly proportional to bond energy and inversely proportional to bond length. Now, because we know that scientists at that point of time were only interested in the inert configuration, the octet rule, but we know there is lot of limitations of octet rule. So I am telling you at this point of time only that whenever covalent bond is formed, actually it is formed due to valence bond theory, which says two atoms approach each other and exist as a molecule because they want to pair their unpaired electrons, and in order to pair their unpaired electrons, orbitals have to overlap. So more be the effective overlapping, stronger will be the bond. So strong overlapping of orbitals always form a strong covalent bond. And we very well know the head-on overlap is called sigma overlap. The sidewise or lateral overlap is called pi overlap. Because head-on overlap is more efficient, so sigma bond formed between two atoms is more stable. Pi is relatively less stable. Because they are directional in nature, so whenever p orbitals overlap, they have effective overlapping, so bond formed is strong. So pp overlapping is stronger, followed by sp, and the minimum is ss overlapping, because s is also a sphere. It does not have a directional property, so its overlapping will be less effective. A very important point, you'll get directly questions from this. Now, similar energized orbital form stronger bonds. For example, if a bond is formed between 2s and 2s, or let's say 2p and 2p overlap, this is more strong as compared to 2p 3p, because similar energized orbitals in nature are supposed to have high bond energy. So this is also a conclusion for us, that if two orbitals that are overlapping are almost equally energized, they are supposed to form a strong covalent bond. Now, the pi and lateral overlap, obviously s, because s is just a sphere, so it cannot have a sideways overlap, but p, so pp sideways overlapping is possible. PD sideways overlapping is possible, and in complexes, in complex compounds, we will see DD sidewise overlapping is also possible. So a pi bond that is sidewise overlap can be PP, can be PD overlap, can be DD overlap as well. Now, a very less important logic for JEE mains, but still I'm discussing this with you, is sidewise overlap is of one more type. That is, apart from sigma and pi bond, there is another bond called delta. Not much asked by mains, but you should know this. Now, what is a delta bond? It takes place only for complexes, first point, and second point is when all the, for a d orbital, when all the four lobes of d orbital sidewise overlap with each other, such an overlapping is called a delta bond. For example, you can clearly see the d orbital, and when the d orbital overlaps with each other sidewise, they forms a delta bond. So now, if somebody asks you which is a stronger bond, obviously the head-on overlap sigma is no doubt the biggest winner. So the most stable is the sigma bond. But sidewise overlapping, who is having effective overlapping? Sir, four lobes overlapping is more, two lobes overlapping is less. So delta bond is actually more stronger lateral overlap than the simple pi bond that we know. One should keep in mind. Now, just to attempt few questions, just read this question and tell me, do you get the answer? Because it's a logic has been asked by JE, but a very simple logic for us. So a very simple yet effective logic is, whenever nitrogen forms a bond with another nitrogen atom, we can clearly see the first bond formed between two nitrogen atom is a sigma bond. So how many electrons required for making a sigma bond? Sir, one nitrogen will use one electron, another nitrogen will use one electron, and they form this sigma bond. So sigma bond we can clearly see the head-on overlapping. Now, the pi bonds, sir, because we know how many electrons nitrogen has in its valence shell. Sir, it has 5 electrons. So in order to attain inert configuration, how many bonds nitrogen has to make? 3, because if sharing 3 will make octet, we very well know this through 9th class basic. So how many pi bonds you have? So 2. Now go to the orbital picture. Sigma bond, let's say, formed along x-axis. Let's say this y is py, this green color is pz. So py, 1 and 1, 2 electrons. Pz, this green one, 1 and 1, 2 electrons. So how many electrons it is using? Obviously 6. So it's a basic JEE asked, and now obviously becomes a basic for us. But how many electrons are used? 6. What is the bond order of nitrogen? 3. So if bond order is high, that's why nitrogen is the most stable diatomic molecule. It is very difficult to break N2 into nitrogen. Therefore, reactions of oxygen are found in nature, but all elements do not easily form nitride because nitrogen do not react. And why nitrogen do not react? Because bond order of nitrogen is 3. Bond order is high, so bond energy will be high, bond will be strong. Again, another question, choose the incorrect order of bond strength. Now, sir, for overlapping, what we have seen, more effective is the overlap, more strong is the bond. If more strong is the bond, more it is stable. If it is more stable, then if you are asked about the bond strength, then its bond strength will be higher. Now, practically speaking, first, whenever you have to check the orbital picture, that which is a stronger orbital overlap, the basic that I'm giving you is, you just count the value of their principal quantum numbers. For example, a third level energy and a third level energy. What is the total? 6. 2 and 3. What is the total energy? 5. Sir, if energy is high, stability is definitely less. So you just go by the principal quantum number first. So if let's say this value is n1, this value is n2, because for one atom and for another atom they may be different. So the value of principal quantum number first you add. So if value of n1 plus n2 is different, so low value will have high stability. Because if energy is less, obviously if energy is less, a system is bound to be more stable. So for example, over here, the total value of principal quantum number is 6. Over here it is 5. Sir, who will form a stable bond? Less energized orbital. So this is definitely correct. And it is saying that also. And we have to choose the incorrect option. So this is a correct option. Now, here the summation of principal quantum number is also 6. Here it is also 6. Sir, if it is same, then now, if n1 plus and n2, that is the principal quantum numbers of the participating orbitals in the overlapping, is same. This is the case when they are different. If it is same, then this is a very important point you should always keep in mind. If the energy level of principal quantum number is same, then DD overlap is the strongest, followed by ED overlap, and minimum will be PP overlap. This I am talking for the overlap when n1 plus n2 value is same. Sir, why it is so? We are directly rushing to the D block elements. I've told you I'll be summing up everything for you. Now, how, sir? Transition elements, when we talk about the D electron cloud, it is mostly belonging to the outermost periphery of an atom. So if nucleus has very less control over their orbitals will be more having much of entropy, and if they have much of entropy, their extent of overlapping, it is like when I am very avara, when I am very free moving. So one free moving person will meet the other free moving person in a larger extent because they are not involved with the nucleus. They are not much involved in the family. So they will be interacting outside more. So point is, DD, when n1 plus n2 value is same, extent of DD overlap is higher, followed by PD, and then the last is PP, because more energized orbital tend to have more effective overlapping. This is a practical fact which you have to keep in mind. Now, some facts you have to keep in mind. Now, sir, because n1 plus because the summation of principal quantum number is same, so PP overlap less, DD overlap more. It is saying that only, so it is also correct. So not an answer for us. Again, 3 plus 3 is 6. 2 plus 3 is 5. Oh, less energy. Now, when the energy, this you will only apply when n1 plus L2 value is same. When energy of principal quantum number is only, dissimilar, the lower energy orbitals will have more effective overlapping because they will be listening to the nucleus more, so they will be having more effective overlap. This is a basic common sense that if energy level is less, if energy inside this system is less, stability will definitely be more. So this is definitely correct because it is correct. So not an answer. Obviously, here n1 plus n2 is 6. Here also it is 6. So DD highest, DD not there. PD yes, PP no. So this should be the exact answer. PD overlap is effective and PP is least effective when n1 plus n2 value is same. So this is incorrect. So an answer for us. A good question. Moving ahead. Now, sometimes it is asked, what is the criteria? Generally, when we move along the period, our criteria is generally electronegativity. Keep this thing in mind. When we are moving along the period, the deciding and dominant criteria is always electronegativity because along the period size decreases. But that decrease is not that much in magnitude, so electronegativity dominates generally. And down the group, because we know atomic size increases and increases to such a large extent that always atomic size mostly predominantly decides all the criteria. For example, if somebody is asking you, you have to arrange the bond energy of X bond, X the halogens, because we know halogen exists in nature in form of X2 molecule. Why? Because of covalent bond formation. What about the bond order? So bond order is 1 only because F bond F is also 1, Cl bond Cl is also 1, Br bond Br is also 1, I bond I is also 1. So bond order is 1 for all of them. But so down the group, what is the criteria? Bond length. So because bond length increases, remember that bond length is inversely proportional to bond energy. Sir, as bond length increases, and we know this increases very large, so bond energy will definitely decrease. So you tell me who has the largest bond length and will be having least bond energy and can be broken easily? I2. So least bond energy is achieved by I2, no doubt. Now, after that, it has to be Br2 and Cl2. And in fact, this F2 should have been here. Now, if you just exclude F2 from your question, the question is very easy for us. If you do not see F2, sir, it is following this trend, which is I2, then Br2, and highest is Cl2. Sir, but you have placed F2 in between. Is it again a factual thing? Although it is a factual data of delta H bond energy, but JEE loves the logic also. In ABCD, you get what is the appropriate reason behind it. Now, the reason is I'm not denying to the fact that it is depending upon bond length. I'm in fact over emphasizing on the fact that fluorine is small, and because fluorine is so very small, and it is valid for mostly if you talk of properties of all second period elements, because of their extremely small size, they always tend to have some anomaly as per the group periodicity. So what does the group periodicity says? That you should have lowest and you should have highest. But because size of second period elements, fluorine in this case, is so very small, that these two fluorine atoms are so much closer to each other that the presence of lone pair repulsion, this is a lone pair, presence of these lone pair repulsions, lone pair repulsion, do not allow them to stay so much close to each other, and hence they break easily. And therefore, if they break easily, amount of energy required to break them is smaller, and therefore the value becomes smaller. But this is a factual thing which you should have to remember, that it is still greater than I2, because in iodine the bond length is so large that it breaks easily. So now this is a practical fact that fluorine loses, but fluorine loses this battle from chlorine and bromine, but still wins to iodine. So this is a very important practical logic which you should know. Now, covalent and ionic bond mostly we have done. Moving to the next chemical bond, that is coordinate bond. As I've already told, it is also called dative bond. The best example is formation of hydrogen isocyanide. So what is hydrogen isocyanide? HNC. So who is the central atom? How do the structure that I'm going to make is the Lewis structure. We very well know what's a Lewis structure. Based on octet rule, we draw the molecules. One becomes the central atom. Generally, who is the central atom? Which has more covalency. What is the word covalency? Your ability to form covalent bonds. How many covalent bonds you make? First, you try to complete your octet. Then, because in nature we know octet rule has got a lot of limitations. Why it has got a lot of limitations? Because actually atom combine with another atom to pair their unpaired electrons. How do we know this? Through valence bond theory. In chronology we'll be going step by step, but this I am in the initial stages only. I'm telling you that atom exists in nature is actually told by the quantum model. When we started knowing atom through quantum model, we started knowing their bonding through valence bond theory, which says atoms combine with each other to pair their unpaired electrons. So coming again over here, this is the central atom, nitrogen. How many electrons it has? Sir, it has 5 valence electron. This is hydrogen. With 1 valence electron, hydrogen tries to become like helium, 1 bond. Nitrogen has got 5. It has made 1 bond, so it will allow only 2 bonds with carbon. So what about the here doublet complete? Happy. Hydrogen is happy. Nitrogen 5 it was having, but 3 has been shared, so 8 octet complete. Now carbon. How many electrons carbon has in its valence shell? 4. How many bonds it made? 2. So 4 plus 2 is 6. So it is still lacking of 2 electrons. So whenever a second period elements are highly electronegative also in their respective groups. Although carbon is not electronegative with respect to nitrogen, but in its respective group, second period element are of highest electronegativity. For second period element, we always do this. Do what? They form a bond, their octet is not complete. How much electrons it is deficient of? 2. That is one pair of electron. Nitrogen octet complete and is also rich of a pair of electron. So this pair of electron from nitrogen is donated to carbon, and this pink colored bond is our coordinate or dative bond. So here nitrogen becomes the donor atom and carbon becomes the acceptor atom. We know through our ionic concept that one site which has a tendency to donate is also called a Lewis base, and one site which has a tendency to accept is called a Lewis acid. Now for chemical bonding per se, for chemical bonding essentially, if you'll ask me, sir, what is the strength of a coordinate bond? Coordinate bond is just similar to that of a covalent bond in terms of its strength. So because this is a covalent bond, this is a covalent bond, this is a covalent bond, so to this pink bond I'm even making just as a covalent bond. But sir, it was just a donation from nitrogen to carbon. How will you satisfy? Whenever you replace a covalent bond with a, whenever you replace a coordinate bond with a covalent bond, always do this. Whenever you replace a coordinate bond with a covalent bond, always do this. Put a plus sign in the donor atom and put a minus sign in the acceptor atom. Let's go and learn to the logic why. Let's say this electron I'm marking as X and this is Y. So initially X and Y was with whom? With the atomic structure of nitrogen. Let's say X is still here, but Y has been transferred to atomic structure of carbon. So if I have received one extra electron, I'll attain a minus charge. If I have lost one electron, I'll attain a positive charge. Nitrogen has how many electrons in its valence shell? 5. One gone, how much left? 4. C4. How many bonds I'll form? 4. Octet complete. Doublet complete. I was having 4 electrons in my valence shell. I received 1. 4 plus 1 becomes 5. So 1, 2, 3. And these white electrons are still as it is. So this is 5. So how many bonds I will wish to make to complete my octet? 3. So this is the perfect picture of hydrogen isocyanide, and this is how you can relate how a coordinate bond is formed just like a covalent bond. Moving ahead. Now, although this formal charge definition is given in NCERT, but through the proper logic of, for example, I have not written any formula over here. You tell me, HCN is a neutral molecule? Yes, sir. I do not see any charge in hydrogen isocyanide. But can you tell me what is the formal charge? Sir, yes. Through basic common sense, I can say hydrogen has a formal charge of 0. It is not having any charge formally, as in partial charge. Nitrogen has a formal charge of +1. Carbon has a formal charge of -1. But because NCERT signifies this formula a lot, so even I'm giving you, but you do not have to learn this formula. This formula is simply formal charge on any atom of a Lewis molecule. If you have drawn a Lewis structure of a molecule, so formal charge on any atom is equal to number of valence electrons minus lone pair electrons, not the pair, electrons, minus half of bond pair electrons. So let us go to some examples. Let me do this example. Let us try and calculate formal charge of this hydrogen. Okay. So I'm calculating formal charge as per the NCERT formula, which is, what is valence electron for hydrogen? 1. How many lone pair hydrogen has? So 0. How many bonds it is making? 1. So bond pair electrons will be 2. So 2 by 2 is 1. So what is its formal charge? 0. Giving you the formula again. Valence electron minus lone pair electrons, not the pair, in multiply by 2 because a pair is formed by 2. and bond pair or shared pair electrons. So because you multiply it by 2, you again have to divide by 2, because this is the definition of a formal charge calculation, not at all used. But still, I'm just making you apply that. Moving ahead, can you tell me about this nitrogen? Okay, let us do it. For nitrogen, if it was free, valence electron it has is 5 minus. How many lone pair it is having? Sir, 0. Lone pair gone. Minus half of. How many bonds it is making? 4. So bond pair electrons will be 8. So this is 1. See, moving ahead. About this carbon, how many electrons when it was free it was having? Valence electron 4. How many lone pair? Now it has 1 lone pair. So lone pair electrons will be 2 minus half of. How many bond pair it is forming? 3. So bond pair electrons will be 6. So this is 3. So this is minus 1. So this formal charge, obviously, you can again do this for this ozone molecule. I'm not doing the formula again, but just making this ozone formula for you. I mean the structure, the Lewis structure. Oxygen. How many oxygen? How many valence electron oxygen has? 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Octet of both of them are complete. What about the another oxygen atom? It is having 6 in its valence shell. So one will be coordinated. A coordinate bond is always like a covalent bond. If you want to replace it, then do it. But when you replace a coordinate bond with a covalent bond, put a plus sign on the donor and put a minus sign on the acceptor. Sir, formal charge seen. So what is formal charge on this oxygen? Marked 1, so plus 1. On this oxygen marked 3, sir, minus 1. On this oxygen marked as 2, sir, 0. So if you apply this formula, you will again get the same thing, but this is a common sense. You should know. Moving ahead. Yeah. So before moving forward to the valence bond theory, let us list the limitation of octet rule, which we already know. The first one is, in nature, various species were found which were having number of valence electrons less than octet. Those are generally called the hypovalent species, like BCl3, BF3, existing nature, but the number of valence electron which boron ultimately achieved is still 6, so less than octet. Greater than octet was also found in certain species like PCl5, like SF6. So this hypervalent and hypovalent species should not exist in nature if octet rule is right, but they were existing, so a limitation. If I'm completing my octet or doublet, I should not have any odd electron, but presence of odd electron species were also found in nature, so an limitation. The octet rule is completely based on the chemical inertness of inert gases of group 18 elements, but then xenon compounds were known to exist in nature, so this rule was completely blown and blasted. And moreover, this rule gives you no information about the shape, which obviously we will get through the VSEPR theory coupled with the VBT. Sir, by telling exact same question has come, you have to tell the number of molecules which follows an exception of 2 octet rule. So let us list them. CO2, sir, CO2 carbon has got octet, oxygen octet, so complete octet, so it is not an answer for us. Sir, NO2, nitrogen, double bond O, then this lone pair coordinated to oxygen, so it becomes an odd electron species. See, it becomes an odd electron species. And if you just go by basic, octet of this oxygen is complete, octet of this oxygen is complete. How I'm trying to make this Lewis structure? First, I'm satisfying the more electronegative atoms, because if electronegative atom is there, it will be existing when you will give me electrons. So, and keeping whom indifferent, that you have to live on your own situation, nitrogen, because it is relatively. So this is a basic idea how you should predict the structure, the Lewis structure of molecules. Obviously you should know them also, but you can predict them also, like I have drawn over here. So nitrogen becomes a species with an odd electron. Its octet is also not complete because it wished to form only 3 bonds with no unpaired, with no odd electrons. But because there is presence of odd electrons, so not following octet rule. So this is option 1 for us. I'm putting a tick. So I'm having, it was an integer type question of 2024. So 1 contribution I've got. What about H2SO4? Sir, okay, sulfur, 1 OH, 1 OH. Octet complete, doublet complete, octet complete, doublet complete. Sulfur has how many electrons in its valence shell? 6. It has made 2. Now it wants to stop. But it again, in order to satisfy the electronegative oxygen, it has to form more bonds. Okay, you can form a coordinate bond also, but still octet rule is anyway violated. So this will also be an example where octet rule is not followed. So an answer for us, so ticking, so it is 2. BF3, clearly I can see it is forming 3 bonds, so 3 plus 3 is 6, not following octet rule, so an answer for us. CH4, octet complete, so not an answer. SiF4, carbon family, 4 bonds, so octet complete, not an answer. ClO2, Cl, 1 oxygen with a double bond, electronegative oxygen I'm keeping in mind. Now, what about because it is ClO2, so I'm having 2 oxygen. So I'm giving a coordinate bond to this oxygen, octet complete, but what about chlorine? Has got 7 electrons. So 1, 2, 3, 4, 5, 6, and this 1 electron will be an odd electron species. So over here, its octet rule is not even followed because it just wish to form 1 bond. So here also octet is not followed. PCl5, 5 as in 5 plus 5 is 10, octet not followed, it's a hypervalent molecule. BeF2, beryllium has 2 electrons making 2 bonds, so it is 4. Again, octet rule not followed, hypovalent species. C2H6, let us draw this. CH3 bond CH3. We all know for carbon octet rule is generally always obeyed. That is the nature of this organic compounds, that is carbon containing compounds. So C2H6 has complete octet, so not an answer. Okay, I'm sorry. We were supposed to tick the species which were having exceptions to octet rule. So this is a tick, this is a tick. I'm sorry, this is a tick. This is a tick. This is a tick because this is an answer for us. This is a tick and this is a cross. I'm sorry. Again, carbon forming 4 bonds, octet complete. So not an answer for us. Carbon forming 4 bonds, not an answer for us. That's it. How many tick we have? 1, 2, 3, 4, 5, 6, 6. So these trouble you have to do during JEE paper also. So you have to be very strict with your whatever basics you have learned. Going to the next question. Which of the following pair of molecule contain odd electrons and an expanded octet? So you should have odd electron and expanded octet. Okay. So this is expanded. No, this is hypovalent. So I want expanded. This has expanded, but no example of odd electron. So not an answer. NO is odd electron. Let us check. Yes, oxygen octet is complete, but nitrogen have this odd electron. So presence of odd electron and expanded octet. We have already drawn H2SO4. Sulfur will have an expanded octet. So yes, this is an answer for us. Again, odd electron, uh, electron deficient. Expanded octet, it is hypovalent. Over here, expanded octet. So only this option has 1 odd electron and 1 expanded octet. Easy, but just whatever basic we have seen, see, JEE directly asks them. Now, which of the following compound contain ionic, covalent as well as coordinate bond? Let us check. Now, this is obviously a salt, forms ammonium cation, NH4 plus and Cl minus. So ionic bond, yes. What about this? Na plus, BF4 minus. So ionic bond, yes. CH3CN, no carbon compound. So this is nitrogen, like the one we have seen, the coordinate example. So this is having no ionic bond. Now, option D is both A and B. So obviously it has got covalent bond and coordinate bond, but no ionic bond. So this is not an answer for us. This has got ionic bond, this has got ionic bond. If we look at ammonium ion individually, how ammonium ion is supposed to be formed? Sir, ammonia giving lone pair to H plus. This is nothing but NH4 plus. So how ammonium ion is supposed to be formed? Sir, ammonia having 3 covalent bonds and then coordinating this to a proton H plus. So it has got ionic bond also, covalent bond also and coordinate bond also. So an answer for us. What about this? This has got ionic nature, NaBF, Na plus BF4 minus. Looking at BF3 gaining electron, what is F minus, sir? Fluorine having 8 electrons because 1 electron is additionally given, so F minus. So this will be coordinated to BF3 and individually it can exist as BF4 minus. So BF3 has covalent bonds and this fluoride ion when coordinating, being a Lewis base, BF3 accepting as Lewis acid, forms BF4 minus. So these two options definitely has both the three types of bonds in them. Moving ahead. So moving forward, let us try and identify these Lewis acids and bases, which will definitely give you too many questions. But I have coupled all of them so that to make the clarity of all the relevant basics of S block, P block. So moving ahead. For example, fluoride ion. Fluoride ion, sir, it is having excess of electrons, so it will definitely be a Lewis base. How about ammonia? Sir, ammonia, because of presence of these lone pair of electrons, will definitely act as a Lewis base. What about water? Water, because of the presence of lone pair of electrons, will also act as a Lewis base. Now, what about CO2, sir? Let us draw CO2 then. CO2, we can very well see this structure of CO2 is telling us that the oxidation state of carbon is +4. Because carbon is through ionic equilibrium, also we know this, that a +4 oxidation state makes this carbon of CO2 very, very acidic and it will require electrons. Therefore, whenever you mix this CO2 in water, what is observed that since we already know water is a base, we'll definitely try to give electron to this carbon. But sir, carbon is a second period element. How many orbitals it has? 2s and 1 orbital of 2s and 3 orbitals of 2p. So there is no vacant orbital. So as soon as these these lone pair of electrons of oxygen are coming into carbon, oxygen will be very happy to take this pi electron because it is electronegative also. So what are we going to have over here? This O becomes O minus. This is exactly this double bond O, and this water molecule, when has approached the carbon of CO2, will definitely give this electron because this electron was initially present in atomic structure of oxygen. So as soon as this carbon has received an electron, but oxygen has attained a positive charge, and oxygen being electronegative will definitely try to snatch the electron of less electronegative hydrogen, and this hydrogen will be carried by this oxygen. So what we got is a beautiful picture of the actual formation of carbonic acid. Just add these number of atoms, we get carbonic acid. So why CO2 is an acidic oxide? Because when it goes to water, it gives rise to an acid called carbonic acid. So obviously the CO2, because it is accepting electrons, so it will act as a Lewis acid. Now, although this picture is giving you a clear idea of how the mechanism of organic compound, because carbon containing compounds are organic compounds, and because we have to know these basics, although this belongs to the reaction mechanism side of it, but because this reaction is largely belonging to inorganic chemistry, hence I have discussed here only. Moving ahead. Now, what about BF3? Sir, boron also is attached with 3 fluorine, has a oxidation state of +3. So boron also has a vacant orbital. Octet is still not complete, so it can also accept the lone pair of electrons in its vacant orbital, and therefore it will also behave as a Lewis acid. Now, what about PCl5? Phosphorus, although we can definitely see it has an expanded octet, but because of presence of 5 electronegative chlorine atom, its oxidation state is also +5. And phosphorus is a third period element, so it will also be having vacant d orbitals, and in those vacant d orbitals, because of such high positive oxidation state of phosphorus, it will also, if somebody is available, if a chloride ion with excess of electron is available, then it can definitely receive that extra electron and forms Pl6 minus. So these are inorganic basics also, but coupled it with because a coordinate bond is formed by a Lewis acid and a Lewis base. So I'm discussing all that theory here also. So what is PCl5 for us? Because it is accepting electron in its vacant d orbital, so it will also act as a Lewis acid. H plus definitely has has 1s orbital vacant, so it will definitely add up lone pair from oxygen of water and form the hydronium ion, so it is also definitely a Lewis acid. AlCl3, it is a Lewis acid because of incomplete octet. What about SiF4, sir? Silicon is a electron precise element like carbon, formed 4 bonds, but it is forming bond with whom? With most electronegative fluorine. And how many fluorines? 4. So again, oxidation status +4. And because of this, silicon will also have an ability that if somebody is available, like fluoride ion. So this fluoride ion can even give electron to silicon, because silicon, like aluminium, like phosphorus, it also has vacant d orbitals, so very well accommodate those incoming electrons and it will give rise to. Now, a basic which I'm telling you is, sir, why you have done 2 minus? Because whenever a central atom is approached by more number of atoms, if the incoming atoms are not very large, like fluorine is not very large, so what structure molecule becomes very stable in nature is the octahedral structure. So in order to form the octahedral structure that we'll be discussing in VSEPR theory, but we should know this also, that in order to form octahedral structure, how many incoming atoms, how many atoms has to approach the central atom? 6. So therefore I have made a octahedral shape of SiF6 2 minus. Now the last one, SO2, is a bit tricky for us, although it's a factual thing also, but I can obviously relate with some of the concepts that you should know. Obviously, SO2 when goes to water, because it's a non-metal and non-metal oxides are always acidic. Moreover, oxidation state is also +4. So it can definitely receive the electron because it will be having vacant d orbitals also. And what acid it will form? It will form H2SO3, sulfurous acid. Sir, so obviously it is accepting electrons, so acting as a acid. But for SO2, you should definitely know this, although this is chemistry of p block element, but including in chemical bonding also, that you can very well learn and understand this if somebody is available. Sulfur also has got lone pair of electrons because it is an element of oxygen family. So number of valence electron in sulfur is 6. So it can also has an ability to donate electron, but do the other person has the capacity to accept it? Although everybody don't have that capacity. But if I take a nitrogen family member which is antimony, this antimony with some electronegative element, so let's say SbCl5. Antimony, Sb is a nitrogen family. New Zealand, Pakistan, Australia, sub antimony. So antimony being connected with 5 electronegative chlorine also has vacant d orbital present in an oxidation state of +5, can definitely be electron deficient and accept these electrons from sulfur. And because sulfur in this case is giving electrons, so it is also act as a Lewis base. So for SO2, my friends, it can act as acid also. Mostly it will act as acid, but it can act as base as well if the other person is ready to accept the lone pair of sulfur. Moving forward. Now, coming to the Born-Haber cycle. What is Born-Haber cycle? Nothing. Through thermodynamics, we know it is just energy conservation. How energy is conserved? You travel from path A to path B. You follow any path, but energy always remains conserved. How we are using this concept? Let us understand this with the common sense of formation of NaCl. Now, we know that NaCl in nature exists as NaCl solid. How this NaCl solid is formed? Firstly, you need a sodium solid. Then you need what? You need chlorine, but chlorine in nature is existing as a diatomic molecule of Cl2 gas. Now, Remember, through thermodynamics, what is enthalpy of formation? Enthalpy of formation is when 1 mole of a solid is formed or 1 mole of a crystal is formed, because NaCl in nature generally exists as a solid. So when 1 mole of solid is formed from its constituent elements in their most stable state or native state, this process is nothing but enthalpy of formation. This is the definition of enthalpy of formation. So if I have to form 1 mole of NaCl, so I need 1 mole of this. But because there is only 1 chlorine, so I'll be needing half mole of Cl2. Now, how I am, this is path A to path B. So how I'm going to apply the Hess law, and applying that Hess law, I'll definitely get a cycle. And that cycle will be termed as Born-Haber cycle, loved by JEE. Now, how to draw the other picture, sir? How it can be taking place? Go to the basics of thermodynamics. Let me again help you with the basics again. Now, first of all, this from point A to point B, here this and the energy is known as enthalpy of formation. Now, the other way how you can reach here is, first of all, if sodium has to form Na plus ion, remember, if I'm supposed to take electron of some species, first I have to bring that species into gaseous state. So first of all, you have to convert the sodium into sodium solid. So here what energy will be used? This will be enthalpy of sublimation. Now, this gas will undergo ionization and forms the desired Na plus ion. So this process is called enthalpy of ionization. What about chlorine? I need chlorine atom, but we have a chlorine molecule over here. So first I need chlorine atom. How can I get these atom? Sir, I need 1 mole of atom. So if I break 1 molecule of chlorine, how many atoms I'll get? 2. But I need 1 mole. So the amount of energy required for bond dissociation, because this much bond energy will give me 2 moles of chlorine atom. So I will be giving half of this energy and be getting 1 mole of chlorine atom, because remember, enthalpy and every thermodynamic quantity are extensive in nature. Extensive as in they depends upon the amount. So these considerations you always have to keep in mind. Now this is chlorine. Now the 1 electron that is given by sodium will be gained by chlorine, and this will be forming the chloride ion, and this enthalpy change is known as electron gain. And once Na plus and Cl minus ion approach each other, we have already seen the electrostatic force of attraction will bring them together, and they will form the solid crystal. So the amount of energy released, the enthalpy change, will be termed as the lattice enthalpy. So if you apply the Hess law, so by Hess law, what we know, by Hess's law, what we know, energy is always conserved. So what, for reaching point A to point B, what was the energy associated? Delta H formation. So this delta H formation will be equal to sublimation plus ionization plus bond dissociation by 2 plus delta H Eg plus delta H lattice. So for the case of simplicity, I'm writing it as 1, 2, 3, 4 and 5. So this will be equal to 1 plus 2 plus 3 plus 4 plus 5. But remember one thing, although this basics we have already dealt in thermodynamics, sublimation is always endothermic, ionization is always endothermic, bond dissociation is always endothermic, electron gain is exothermic, and lattice, because I'm going from gas to solid, so obviously energy will be released. So over here, these 2 processes will be exothermic, while these 3 processes will be endothermic. So whatever, obviously, if it is forming in nature, this delta H formation will come out to be negative, because if a compound is existing in nature, then obviously delta H formation, if I'm getting stable, I'll be releasing some energy. So, but this delta H formation is not negative for all of the species, but for mostly for the crystal which are existing in nature freely, it is generally electronegative. So this is a very easy Born-Haber cycle. Now, can you draw this Born-Haber cycle for aluminium oxide? Let's check. Yeah, so just to save us a bit of time, I've drawn this Born-Haber cycle for aluminium oxide, and as you can clearly see, aluminium, 2 moles of aluminium, because what is the most stable state for aluminium? It is solid. Oxygen exists as O2 gas, so 3 by 2 of O2 gas will definitely form this 1 mole of aluminium oxide. So this will be enthalpy of formation. Step 1. So this enthalpy of formation will be equal to sublimation, but because it is again an extensive property, so will depend upon amount, because we need 2 aluminium, so we have to sublime, change the solid to gas, both those 2 moles of aluminium. So twice of sublimation enthalpy will be used. Now, electron gain, aluminium is here in +3 state. So how many electrons I have to remove? 3. So ionization energy 1 plus second ionization enthalpy plus third ionization enthalpy. So the summation will be ionization energy total. Keep this thing in mind, because that NaCl1 everyone predicts, but for this, these are some good level questions which will definitely require what I'm actually telling you. So this is the total ionization energy required to remove 3 electrons. But how many aluminium you have to ionize? Is 2. So this whole total will be multiplied by 2. Now, if I have oxygen in form of O2 molecule, so if I break 1 mole of oxygen molecule, I'll get 2 atoms. How much atoms I require? 3. So bond dissociation energy into 3 by 2, because 1 mole of bond dissociation energy will fetch us 2 moles of atom. We need 3 moles of atom, hence the factor 3 by 2. Now, for electron gain, this oxygen is existing as an oxide ion, so it requires 2 electrons to be gained. So electron gain enthalpy first plus electron gain enthalpy 2 will be the total electron gain enthalpy for this oxygen atom to gain those 2 electrons. But how many oxygen atoms we need as oxide? 3. So this whole thing will be multiplied by 3. And finally, when these gaseous ions are formed, they will obviously electrostatically attract to each other and forms this lattice by releasing this lattice energy. So again, your Hess law will be, formation will be equal to 1 plus 2 plus 3 plus 4 and plus 5, where these 2 steps will be exothermic as in case of NaCl, but a very good knowledge of Born-Haber cycle indeed. Now, moving ahead, this brings us to Fajan's rule. Now, what is it? We have recently discussed that ionic compounds and covalent compounds are formed by transfer of electron or sharing of electron. Now, in nature, when we have gone and observed those molecules, those compounds, no compound is having perfect ionic nature or perfect covalent nature. Everyone has a blend of both of them. How, sir? This was explained by Fazans and loved by JEE. For example, we very well know through class 9th only, we know NaCl is an ionic compound, right, sir? So if NaCl is an ionic compound, sodium has lost electron, formed sodium cation, chlorine has gained electron, formed the chloride ion. If you look at the distance of nucleus, this is nucleus of sodium, this is electron of sodium, this is nucleus of chlorine, this is electron of chlorine. Now, if you just check, because generally the anions are of larger size, so if you just check distance between nucleus and valence electron of chloride ion is almost not very much as compared to the distance of nucleus of this cation from the electron of the anion. What happens is, sir, plus attracts minus. So don't you feel when this cation is getting smaller and smaller, it also will have an affinity, a tendency to attract the electron of the anion, the larger anion? Similarly, if cation gets smaller and smaller, obviously its tendency to attract the electron of anion will increase to a larger extent, and you will get such a picture where the electrons of the anion are in close proximity, are in influence of the cation as well, and therefore there is a polarization of the anion which takes place. What is a covalent bond? This pink colored electron, which is actually belonging to anion, it is in influence of the nucleus of cation also, and I'm not denying to the fact that it is in influence of nucleus of anion also, sir. So this is a pattern of sharing. This electron is actually being attracted and shared by this nucleus also and that nucleus also, sir. This is a factor of sharing. So this is a factor of covalent nature coming into this ionic compound. So what we say, what we refer to this is, it is just the polarization power of cation and polarizing ability of anion. If cation is strong enough, it will have a high polarization power. If anion is large enough, it will be having a tendency that you polarize me. You so we to in English we refer it as polarizability of anion. So if polarization power of cation is high and polarizability of anion is high, then anion will get polarized and cation will polarize the anion, and then in this case the ionic compound will attain covalent character. And if ionic compounds attain covalent character, then all the properties of ionic compound which we have just compared in the table, ionic compounds have high melting and boiling point, they are soluble in water, they are hard, so they form a stronger lattice. So whatever properties, if ionic character of a compound is more, it will have more of those properties, because in JEE question is generally which is more soluble. So in order to come to their solubility or comment about their melting and boiling point or comment about their lattice, we always have to compare their percentage ionic character. You do not have to re- calculate using the formula, because the formula also we have learned in periodic table, but that formula you do not have to apply. You can simply apply this logic of Fajan's rule. So I'm finally summing it up. What does Fajan rule say? Polarizing power of cation, if higher, it will polarize the anion, and if the anion gets polarized easily, then that particular ionic compound will attain a covalent character. I've written all these theory over here, and at last I'm just going to mention you that how to calculate the polarizing power of cation with the charge density. A cation, more be the charge density. Remember what is charge density through atomic structure? I'm explaining again. Charge density is the ratio of charge upon size. More is the charge, more is this value of phi, which is the charge density, the potential density of the cation to polarize the anion. More be the charge density, more be the value of phi to this charge density. For Fajan's rule, I will always refer to it as phi. So more will be the value of phi, more will be the polarizing power of cation. It will largely depend upon the charge, and once the charge is same, then you will go and check the size. So whoever will have the lower, has the smaller size, will have the high value of polarization. Moving ahead, and you will find a number of questions. What I have done for you, I have just coupled all those questions for you, so you just have to sit back and at least by heart this theory, because this will help you to do number of questions. Moving ahead, coming to the factors affecting polarization, first is the size of cation. We have already discussed, so let us summarize. Let me summarize this for you. So smaller be the size of cation, obviously more will be its charge density, that is phi, more will be its polarization power, and if it has a high polarization power, it will polarize the anion and will attain covalent character. So more will be the covalent character. If an ionic compound has more covalent character, then obviously its ionic character is lesser in percentage. For example, if you are supplied with such a question and you are asked that which is most ionic, if I'm most ionic, I'm again repeating it. If I have got ionic character, I will have a high melting point, I will have a high boiling point, I will be having a good lattice, I will be more soluble in water, because these are the general properties of an ionic compound. So if ionic character is more, these properties will be more. So any of those options will be asked to you, any of those properties may be asked to you, but what you have to apply is, in order to check the ionic percentage in a ionic compound, you have to apply Fajan's rule. More will be the Fajan's property, more will be the covalent nature. So coming again to this question, sir, anions are same. Okay, so who is the point of difference? Cation. Cation charge is, sir, alkali metals, so all +1. So it will be decided by the size of an ion. Because lithium is the smallest, so it will have the highest covalent nature. And what are you asked? The covalent nature. So because lithium is smallest, so lithium size is smallest, so its polarization will be highest and its covalent character will be highest. So if you ask the covalent character, so LiCl will have the highest character and it will go on decreasing down the group. Now, again, charge. So charge is the most dominant factor. First we check charge only. So more be the charge, or maybe less is the size, more will be the value of charge density. More be the value of charge density, mole is the polarization power of cation. If cation is polarizing, it will create more of covalent nature and obviously less of ionic nature. Simple. Just apply this. Again, we have to tell the covalent character, so which has got the higher charge. How to calculate charge? I mean, the cation and anion charge, you just multiply, because actually it is the magnitude of charge. So what is value of Q1, Q2 over here? 1 plus 1 into, that is 1. So this is 1. This is 2, 2. So this is 4. This is 3, 3. So 3 into 3 is 9. This is 4, 4. It is 16. So obviously, with the product of charge on either ions, you can definitely say, because this has got the highest charge, so its covalent character will be highest. And covalent character of NaCl. So among these four, who will have high melting or boiling point? Generally, who will be more ionic? Who is more ionic? Who is the least covalent? Who is least covalent? NaCl is least covalent, hence least covalent, hence more ionic. So you can tick that yes, NaCl will have the highest ionic character, so generally it will have high melting and boiling point. Moving ahead. Now, so for ionic character, we are doing what? We are doing the Fajan's rule factors. Now, next is, sir, anion. Obviously, we have already seen anion has to be large enough in order to let the valence electrons of anion to go as far as possible and get polarized. So if anion size is large, its polarizing ability will be large, and obviously it will get easily polarized. So the covalent character will obviously increase and ionic character will decrease. Again, a question. Cation is same, sir. Anion charge is same. It will come to the size. Who has the largest size? Iodide. So because iodide has the largest size, so it have the highest covalent nature, and NaF will have the least covalent nature. So covalent order is this. Now, charge, again, sir, if charge is more, for charge you have to we do that charge density for cation. For anion, it is larger in size and more is its charge. If charge of anion is more, obviously the charge of cation will also increase. So my point is, if charge of anion is high, moreover its size is also high, then obviously its ability to get polarized will obviously increase. So polarization will increase, covalent character will increase, and ionic character will definitely decrease. Let us understand this with a question. LiF, so the lithium oxide and lithium nitride. Cation is same. Which anion has the largest size? N3 minus. And obviously, who will have more 3 minus? For isoelectronic species, we already know this. More be the minus charge, more will be its size. So obviously, if I have more charge, my size will be more. And if my size is more, obviously, my polarizing ability will be high. And I will be attaining more of a covalent character. So this will have the highest covalent character, where LiF in these three will have more ionic character and less of covalent character. Moving ahead. Now, it also depends upon the type of cation. So cation, you have already told us to see its charge density. Charge density you can see. But the type of cation also matters, because what is the job of a cation? So to polarize. Polarize whom? Polarize the anion. So polarizing ability also depends upon my effective nuclear charge. Now, what I'm telling you, first let me introduce these type of cations to you. So the first type of cation that I'm introducing is the inert configuration. Sir, alkali metals, there's lose electron to do what? To attain inert electronic configuration. So over here, I am talking about the group 1, that is alkali metal, and group 2, that is alkaline earth metal. What electronic configuration they attain? Sir, of an inert gas, because they come in +1 state, they come in +2 state. So what electronic configuration they attain? Inert configuration. So to those cations I am referring as cations having inert gas configuration. Now, what is a pseudo inert gas configuration? Just like attained by the transition elements like zinc, cadmium, mercury. What oxidation state they acquire? +2. So after acquiring that +2 oxidation state, their inner shell becomes completely stable. That configuration in which they have inner shell as in ns2 np6, and the for zinc, if 3s electron is gone, the 3d is fully filled. So that configuration is termed as an inert configuration. Similarly, just before this 12th group, you have copper, silver, gold. They acquire pseudo inert configuration by losing how many electrons? So they come in +1 state. So cations having these configuration are termed as cations with pseudo inert gas configuration. Now, what are non-inert gas configuration cations? I mean, just go to 6th period. Why 6th period I'm saying? Because in 6th period, after lanthanum 4f, the lanthanide series is firstly filled. So just go to this from mercury. From mercury I'm talking. Mercury, who is the next element after mercury? The boron family, Began, Alu, Gajan, and Thela, so that is thallium. Then after boron family, carbon, Kashi, Shankar, Parvati as in Pb as in lead. Then after carbon family, we have nitrogen family, New Zealand, Pakistan, Australia, sub, Bikau as in bismuth. Now, mercury attains this pseudo inert gas configuration. When how it attains this pseudo inert gas configuration? Mercury acquires a state of 0. Mercury exists as a 0 oxidation state element. Helium exists as a +1 oxidation state. Helium forms compound in +1 oxidation state because it is boron family. So Began, Alu, Gajan, Thela, boron family has how many electrons in its valence shell? 3, but it prefers to form a compound in +1 state. Similarly, lead prefers to form a compound in +2 state. Similarly, bismuth prefers to form a compound in +3 state. Why, sir? Their group oxidation state is, you must have observed, I have subtracted 2 from their group oxidation state. This is nitrogen family. So how many electrons it has? 5. But what oxidation state I have chosen? 3. This is carbon family. So how many valence electron? 4. But what I have chosen? -2. Boron family has 3 valence electron, but what stable oxidation state I have chosen? +1. Mercury, zinc, cadmium, mercury, they have how many electrons in its valence shell? The 6s2 electron. But what oxidation state I have chosen? I have not taken out any electron from mercury. And I'm saying that mercury having a 0 electronic configuration remains more stable in nature. Now, why I'm saying this? This pseudo inert gas configuration, what happens is, if you just observe, although this is inert per effect, I will be discussing this inert per effect also, but just in order to make you learn first, and then we'll discuss in the next slide as inert per effect, what is it, why they prefer this oxidation state. But I'm just first categorizing these 3 types of cations. Now, sir, the type of cation you have introduced, but it is still not clear why you are telling us this. Because a non-inert gas configuration cation, non-inert gas configuration cation like these 4. These cations have a tendency to increase the covalent nature of any ionic salt they form, followed by the pseudo-inert gas configuration cations, and the least covalent, least polarizing power will be attained by the cations having perfect inert configuration. For example, what I'm saying is, if question is asking you to arrange the covalent character of BaCl2, HEgCl2, then PbCl2. PbCl2, lead is in +2 state, a cation belonging to this non-inert gas configuration, so it will be most covalent because polarization power of such cations are largest. After that, pseudo-inert gas configuration, just like mercury in +2 state, okay. So you can take this mercury in +2 state, this one. Instead of 0, this is mercury in +2 state. I'll be explaining this more when we'll be discussing inert pair effect, but just to put basics in place. So this is a non-inert gas configuration cation having the highest polarization power, followed by pseudo-inert gas configuration Hg, because here mercury is in +2 state, and the alkali and alkaline earth metal are the inert gas configuration cation. So the D block cations have large polarization power than the S block and the sixth period element, because their Z effective is large. They are having the highest polarization power. Now, if I am discussing about the polarization power, the same logic applies for diagonal relationship also. Because to all the anions, how a cation is treated? Cation is just treated by all the anions as a center which is electron deficient. So this electron deficient cationic center will attract every minus around it. So I will be considered by my charge density, my polarization power. And if two cations, although they have different nucleus, but if their polarization power is same, so to the world, to the outside world, they will be appearing as same cation because their polarization power is same. So sir, do some different cations also can have same polarization power? It has been observed in the periodic table that polarization power of lithium and magnesium are exactly the same, although charge on magnesium is +2, but its size is also large, so ratio of charge upon size is approximately same as that of lithium cation. Similarly, charge upon size ratio of beryllium +2 is approximately same to that of aluminium +3. Similarly, charge upon size ratio of boron +3 is approximately equal to that of silicon +4. Therefore, a diagonal relationship is observed between these second period and diagonally placed third period elements. You will be getting much of the questions relating to this diagonal relationship, where you just have to know that if lithium is doing something, so who will do the similar chemical property? Magnesium. Beryllium will have similar property as that of aluminium. Boron will have similar property as that of silicon. So this diagonal relationship is also a byproduct of the similar charge density, which is responsible for the polarization power of cation. Now, one thing we introduced but we have to put more light on is the inert pair effect. Now, why I am discussing this inert pair effect independent, I mean in between, not independently, because this is a concept which is involved with almost all p block and inorganic elements. So that's why I have also introduced this topic in between only. Now what is it? Just check. The same thing which I have told you. Mercury, thallium, lead and bismuth, lower oxidation state is more stable, because I intentionally was writing their oxidation state by counting the number of valence electron and then subtracting by 2. That I'm telling you now this I always used to do. Whenever I want to remember the stable oxidation state of the sixth period element, that is the p block element present at the last, including mercury, because mercury will be the next element just before the p block elements, the 13th group. So I always do this. What I do, I take out their number of valence electron, subtract it by 2, and whatever oxidation state, obviously because I'm subtracting by 2, so oxidation state will be lesser by a factor of 2, and that will be their most stable state. And why it is so? The lower oxidation state is stable because of a phenomena which is inert pair effect. Again, giving you the trend. You should remember this by heart. Mercury, although it can give the 2 electrons, but it does not acquire +2 state, it acquires 0 state. Now I'm telling you, sir, but over there you have given HgCl2 mercury. There may be certain compounds in nature which are formed by non-spontaneous forced reaction. So am I saying this compound is stable? No. I'm just saying, I'm just asking, question is just asking who is more covalent. They are not commenting about their stability. Maybe this HgCl2 is not stable, but if at all it is formed at such some condition, then question may be asked, okay, that I have formed this compound. Now tell me who's more covalent. So for that we have gone to this basic, but now I'm telling you, mercury always wishes to be in zero oxidation state. Similarly, helium, down the group metallic nature increases, so they should give electron. So these p block elements, they all want to give electron, but how many electrons they want to give? The group oxidation state -2. What is the group oxidation state for helium? It is a boron family, so it is 3. So they will definitely want to give electron, but how many? Group oxidation state -2. Carbon family, group oxidation state 4, but showing -2, that is +2. Nitrogen family, bismuth, nitrogen family has 5 electrons in its outermost shell, but bismuth does not want to be in +5 state. It wants to form compound in +5 -2, that is +3. Why, sir, this -2 -2 is you are again telling? Now, point is, we already know periodic table. I have already given you the reason also. Before filling of 6 period element, who is the very first time filled the complete 4f subshell? The lanthanoids, because they are filled, and when the mercury, helium, and when these elements are supposed to be filled, their nucleus is increased by a factor of 14. Moreover, the shielding of 4f electron is not poor, it is very poor. So their Z effective, their effective nuclear charge is very large. So if my effective nuclear charge is very large, won't I attract my electrons to a much larger extent? Yes, sir, you will do. And if I attract my valence electron to much larger extent, then I will not allow them to be given out easily. So what I'm saying is, if I'm talking precisely, I'm talking for this inert pair effect is precisely the very first property to which inert pair effect is applied is to the p block elements. Now, to these p block elements, you can very well see what is the electronic configuration of helium, sir. 6s2, 6p1. What is it? 6s2, 6p2. What is of bismuth? 6s2, 6p3. So they down the group metallic nature increases, agreed, but because their Z effective is so large and penetration of, we already know this through periodic table, that S and P, S has a higher penetration effect. Penetration as in it is more embedded within an atom and hence more attracted by nucleus. Moreover, Z effective is also increased. So this increased nuclear charge will not allow these ns electron to be participated easily. Hence, what will be my oxidation state? Group oxidation state -2. These 6s electron will not participate. So helium will show an electronic configuration, and helium will form compound in +1 state. Its +3 state is not stable. If at all it has formed any compound like that of mercury, if at all it has formed that compound in that particular state, then it will try to come back to the most stable oxidation state which it is incomfortable to acquire. Similarly, lead attains lead attains an oxidation state of +2 to form its compound, not +4, because these 6s electrons are much influenced by the increased nuclear charge. So is the case with bismuth, not the state. And so is the case with, my friends, mercury. That's why over there I prefer to write 0 and not +2. But if it is formed, then that mercury in +2 state will also be termed as a non-inert gas configuration compound. Now, moving ahead. The reason which I have just now told you regarding the inert perfect, I've already given that for these elements, 4f orbitals are fully filled. shielding sigma of these 4f is very poor, so Z effective is very strong, and due to this reason electrons of 6s orbital feels more attracted towards the nucleus, and because they are more attracted, so they are not given out easily, and hence 6s electron do not take part in bonding, and only np electrons take part in bonding, because down the group metallic character increases. So obviously I will give electron, but what electrons I give? I give the valence electron, the inner shell electron. Now it is so much deep embedded that 6s electron is not treated as a valence electron, it is treated as an inner shell electron. An inner shell electron never participate in bonding, only valence shell electrons participate in bonding. Moving ahead. Now, so let's say, because now we know inert pair effect. Now, I'm giving a good question. It is said that SnCl2 and HegCl2 mixture does not exist in nature. If you make a mixture and sell a bottle, your company will be blown, because that mixture will not be present as that mixture. It is gone. It is converted to something else. Why? Do you have any? Sorry, it is an inorganic fact. Now, after inert pair effect, this fact you already know. How, sir? See, SnCl2 when mixed with HgCl2, we very well know mercury do not want to be in +2 state. Mercury wants to acquire a zero oxidation state. So what mercury will try? Mercury will try to come from +2 state till 0 state. So if my oxidation state is getting decreased, what I'm supposed to get? I'm supposed to reduce. So HgCl2 will get reduced by reacting with this species. So if I'm getting reduced, you have to oxidize, you have to get oxidized, because you have to be the reducing agent then. So if this has to be the reducing agent, it itself has to get oxidized. Can't you see that tin will definitely love to get oxidized to +4 state? Why? Because tin belongs to which group? Sir, tin belongs to Kashi Gaye Shankar Parvati carbon family. What is the most stable oxidation state of carbon family? +2, but only for the 6th period element, because inert pair effect is actually applied for the 6th period element, not above it. So we have tin above lead. So for tin, which is the more stable oxidation state? So +4, because this increased Z effective factor is valid for lead. Tin has not got that much of increased nuclear charge. So inert pair effect is actually and largely applicable for the heavier member of the p block element, the element present in the 6th period, not above it. And because this tin is a carbon family element and down the group metallic character increases, so it will try to give electron. And what electron? Valence electron. So what is valence electron for carbon family? 4. So tin has a more stable oxidation state of +4, so it will definitely want to get oxidized and acquire that state. So if these are mixed, they will react to form that compound, and this will not exist. It's a very important question. And moving forward, now let us discuss some applications of Fajan's rule. So first application discusses about the thermal stability of any ionic salt. Now first let us be clear on this conclusion that any lattice is strong when it is formed by cations and anions of similar size. For example, when you are setting up your suitcase, when you will be filling it with maximum efficiency, when you fill your clothes in a pattern, in a specific order, if you just randomly put your clothes inside your suitcase, then the efficiency of that particular packet will not be high. Similarly, when a salt is formed, a salt having strong lattice can be entertaining more amount of heat, so it will be thermally stable. But if a salt is formed by an anion that is polyatomic, so a polyatomic ion is large enough. If it is large, then it can form a stronger lattice with a large cation. With a smaller cation, the smaller cation will try to snatch some of the atoms of the large cation. Like for example, carbonate is a anion, but it is a polyatomic anion. Carbonate has CO3 2 minus. So suppose a small lithium cation is forming a lattice with large carbonate ion, then there is a dissimilarity between the size of ions. So lithium cation will snatch away the oxygen from the large carbonate ion and will definitely keep aside by forming lithium oxide. So such solids, such crystals are not very stable to heat. So they are thermally less stable. This is the basic logic that I'm first telling you. But for questions, I'm giving you a trick also. And this is the first application with the trick. Thermal stability of any, you just see the polyvalent, if the salt is containing a polyvalent anion, you just directly go to the value of phi, because the anion is polyvalent, so lattice will be definitely weak, because anion is small, cation may be small, maybe small, maybe big, maybe small, so you are not confident about the size. So when anion is large enough, there is always a disparity in its lattice. Its lattice is generally weak when anion is large enough. Why anion is large? Because it is polyatomic. So when this anion is large, the lattice is weak, and if lattice is weak, you should only apply the polarization of the Fajan's rule that we have learned. How, sir? This is a salt. Let's say carbonate salt. Number of questions you will get like this. I'm just summing all the questions with this small trick. Anion is large enough? Yes, sir. Apply Fajan's rule. How, sir? Calculate phi. What is the point of difference, sir? Cation. Cation is lithium, sodium, potassium, rubidium, cesium. Charge is same, then it will go to size. So, sir, if radius is small, then phi will be large. If phi is large, polarization is large. If polarization is large, covalent character is large. So if covalent character is large, ionic character is less. If ionic character is less, my melting point, boiling point, thermal stability will also be less. So lithium will have least thermal stability and it will keep on increasing down the group. You can do this. This is a one type of question. You can do the same thing because all the anions, sulfate, nitrate, carbonate, bicarbonate, all these anions are large enough. So if they are large, who will decide their stability? Fajan's rule. How to check Fajan's rule? What is the point of difference? Cations. For cation, apply the rule of phi. Like for example, in this beryllium magnesium, charge is same. Again, go to size, small size, high phi, high polarization power. So if high polarization power, high covalent character, more be the covalent character, less is the ionic character. If ionic character is less, my lattice is weak. My lattice is weak, so I will easily get heated up and destroyed. So my thermal stability is less, and thermal stability will go on increasing down the group for all such types of salts. So we have done too many questions, including that of S and P block elements. Now, second application becomes the thermal stability. Sir, if anion is monatomic, then again giving a reason. If anion is monatomic, then also you have to check the strength of the lattice. But now you will check the lattice. Sir, how to check the lattice? Initially only when I have told you ionic compound form lattice, ionic compound forms strong lattice. Why? Because sir, Coulombic force of attraction. What is Coulombic force of attraction? So lattice enthalpy, this delta H lattice is nothing but product of charges. And okay, the formula, the Coulombic force of attraction has square in it, but for the case of periodicity, I'm telling you that lattice enthalpy is directly proportional to charge. The more first you calculate charge, more charge, strong lattice. If charge is same, then go to radius. The same principle of charge density. But here I'll be taking charge first and radius, and this will be giving us the value of lattice. So whoever has the higher lattice will be having strong lattice, and strong lattice will resist high temperature and will be stable. Over there, we have included this charge density for calculation of phi. Here we are again, basically we are doing charge density only, but this charge density we are implying with the lattice enthalpy. Like in trigonometry also, you learn some formula and then you apply that formula in n number of questions. So this in this side of chemistry also, I'm asking you to learn this much, that if an ion is large, you calculate charge density, but charge density you calculate to find the percentage ionic and covalent character. That is application of Fajan's rule. But here you again calculate charge density, but you calculate charge density and then that charge density will also be making the lattice strong. And if lattice is strong, so thermally it can withstand heat. So it will be thermally stable. This is what case? This is case when an ion is small, monatomic. Now, for example, let us do some examples. Let's say a question is asking us that lithium halide and cesium halide down the group, you have to compare which is thermally more stable. Easy. Go to the lattice because ion is a monovalent halide ion. It is not polyvalent. And ion is common, sir. Okay. What is difference? Cation. How to calculate, sir? Charge. This is also +1, -1, +1, -1. So Q1, Q2 is same for all salts. Go to radius, which has a smaller radius. R is smaller, so its lattice is weak. Lattice is weak, so thermally unstable. Its R is high. Okay, I'm sorry. Its R is less. If R is less, lattice is strong. If lattice is strong, it is thermally stable. Because lattice is small, because radius is small, lattice is high, so it is thermally most stable. And cesium halides are thermally least stable. I'm just going by basics now. When Q1, Q2 is different, obviously charge will dominate. This is +1, -1. So here Q1, Q2 is 1. Here Q1, Q2 is 4. This is +3, -3. So Q1, Q2 is 9. This Q1, Q2 is 4, 4, 16. More be the charge, more is the lattice. Strong is the lattice, more is their thermal stability. So I'm just going by basic, but this basic you should always remember and then apply to n number of questions. Moving ahead. Now, thermal stability of again monatomic. One more example. When Q1, Q2 and R, let's say both are different, sir, what is dominating? First you calculate charge only. So what is charge? 1 into 1, 2 into 2 is 4, 3 into. So this is also easy. Now you can, like with similar application, you can do number of questions. So I'm keeping number of questions limited, but number of logic will make you solve n number of questions. So because charge is high, so lattice is strong, so thermally it will withstand high amount of heat, so thermally it is more stable. Moving ahead. Now, next application is aqueous, radius of aqueous ion. Sir, what is an aqueous ion? Now, first understand the hydration first. In thermodynamics, I have discussed, but I'm again telling you. What is hydration? Sir, we very well know. Ions, ionic compounds dissolve in water. Why? Because why Cl minus and Na plus was forming a solid? Because they were getting attraction. If they are getting attracted by solvent molecule, then they'll go with solvent molecule, and solvent is in which state? Liquid state, aqueous state. Therefore they dissolve in that particular solvent, because this O minus will surround the cation and hydrate the cation. This delta positivity of the hydrogen of water molecules will surround the anion, and this will become the size of the hydrated anion. Now, why these cations and anions are attracted by water molecule? Because again there is attraction of plus minus, and this plus minus attraction is actually termed as the hydration of ions. So hydration of ions also depend on what? On the charge density of ions. So again, charge upon size. So who will be dominating? Charge. And if charge is similar, then you will start comparing the size. So let's say I'm a cation. Let's say now we are comparing the radius. Sir, what type of hair? This photo you have not shown. See, my size of sodium is this much, the small ball. But when I'm introduced in water, I'm greatly and hugely surrounded by water molecules because of the Coulombic force of attraction between water molecules and me. So the size of hydrated ion becomes large when it is getting more hydrated. Similarly, an ion also can get hydrated. So the gas size of gaseous ion and size of hydrated ion is different. This is the size of hydrated ion, the green colored one, and this is the size of the gaseous ion, this small one. So gaseous ion and hydrated ion have different sizes. This picture is making you that clear. Now let us compare the size. So radius, order of radius. For example, alkali metal cations. Lithium is smaller, so lithium cation will be smaller, the gaseous cation. Cesium cation is larger in size, the gaseous cation, that from the periodic table. So we very well know lithium is smallest and cesium is highest. Charge on all these cations are equal. So if charge is same, who will decide their hydration extent? Their size. So who will get heavily hydrated? Whose size is small? Whose size is small? Lithium size is small. So lithium, when goes into water, become very heavily hydrated. So water molecules will circle around the lithium cation and will make it very, very, very large. So size of aqueous lithium ion is much larger than that of size of aqueous cesium ion. This you have to definitely keep in mind. Similarly, let us take another example. Na plus Mg plus 2. Sir, hydration enthalpy. We do not have to compare the gaseous size. So again, for the aqueous size, what depends? And the extent of getting hydrated depends upon charge density. Charge density is charge upon size. So here obviously charge will dominate. If charge is same, then we see the size. Sir, more charge, so more hydrated. Least hydrated. What about the anions? Same logic. Charge is same. Lower be the size, higher be the hydration. So if I'm heavily hydrated, I'll be surrounded by more water molecules and my hydrated size will be high. Size of hydrated iodide will be least. Now the ionic mobility, these all are factors directly or indirectly related to the value of charge density. So therefore discussing with Fajan's rule. Now, if there is a race between two people, one person is I'm fit, one person is fat and someone is fit. Someone is one is fat and someone other person is thin. Who will win the race? Generally, the thinner person. The person that is fat will lose the race. Similarly, if you want to calculate the mobility, the extent by which an ion can move, so a heavy ion cannot move. So point is, more be the size will make me very big, and fat people can't move. So if size is high enough, my ionic mobility will be less. So coming over here now, first let us do NaCl and KCl. Sir, hydration, check their hydration. Cl common, so check Na plus and K plus. In gaseous state, Na plus is small, so its hydration will be high. So hydrated size of K plus will be small. Because K plus is small, so it can move fastly. So who will be having more ionic mobility? KCl ions. Now here, sir, charge is this is also plus 2, this is also plus 2. Now, but over here you can compare the Z effective. The Z effective, zinc, cadmium, mercury. We know lanthanide contraction. So the Z effective of mercury is large enough. That's why its size is not increased. It is almost equal to that of cadmium because its Z effective is increased. So if my Z effective is increased, I will attract more water also. So I'll be heavily hydrated, and because I will be heavily hydrated, I will be bigger in size as aqueous ion, and I can move slowly. So my ionic mobility will be less. Ionic mobility of Z and Cl2 will be larger. Moving ahead. Again, hydration energy is the same. If I'm getting hydrated, I'll release more energy. So Li plus, lesser be the size, so it is getting heavily hydrated, it is getting least hydrated. More be the charge, more is the hydration. So this is heavily hydrated, will release more amount of hydration energy. This Na plus will release less amount of hydration energy. And obviously we can say fluoride ion, because they are small, will release more amount of hydration energy. I minus, the similar thing that we have done. Moving ahead. Now, next is, okay, solubility. One thing, lot of question comes. I'm just summing all those questions in a packet. All the ionic salts are generally soluble in water. Not always. Why? This depends upon the lattice we have already discussed. So if my lattice is strong, if my lattice is strong, then the hydration enthalpy. What is hydration enthalpy? Amount of energy released. What is lattice energy? Amount of energy required to break the solid. So required energy is endothermic to break the lattice. Hydration energy is amount of energy released. So go by money logic. You are investing. You are an investor. Plus is your money that you are putting into the business. Minus is the money after putting an investment, you are getting some outcome. So if your investment is high, then the return. Will you do that business? No. So will that salt be soluble? No, because its lattice is strong. Hydration is not that much high. So if this value is large, then such salts are insoluble. And why salts are generally soluble? Because generally the amount of energy released, that is hydration energy, is larger in magnitude than the amount of energy required to break that particular lattice. So money minded, how we are thinking, the investment that we are doing plus if we are putting in 100 rupees in the company, how much we are making? More than 100. So anybody will invest in that particular company. So that particular salt will get easily dissolved. So this is the basic law of solubility of ionic solids. Now, what I am trying to mention over here is you can also have a trick. This is the logic that I've given. But now I'm giving you a trick also. What is the trick? Solubility always increases down the group. Solubility always increases down the group. When? These two cases. Whenever you find anions of oxide, sulfide, fluoride, oxalate, and hydroxide, remember them, these five: oxide, sulfide, fluoride, oxalate, and hydroxide salts of any metal, solubility always increases down the group. A very, very, very important trick for many questions. Now, this is one case when solubility increases down the group. The second case is when number of cations is larger. When number of cation is larger than number of anion, in such cases also, irrespective of whatever anion is. Here I'm being specific about the anions. If these anions are there, solubility definitely increase down the group. But whatever be the anion, if number of cation in that particular salt is more than number of anion, then also that is the case when solubility generally increases down the group. This is a very great trick that I'm giving you. In all other cases, solubility decreases down the group. Sir, apply this. Not one question. I'm giving you a huge number of set for that. Now, let us discuss them one by one. For lithium, sir, lithium carbonate and cesium carbonate. Carbonate is not that particular anion. No, sir. But how many cations you have, sir? 2. So number of cation is greater than number of anion. Just check. Haan, sir. Lithium is 2, carbonate is 1. Sodium is 2, carbonate is 1. Potassium is 2, carbonate is 1. So obviously number of cations are more. So when number of cations are more, solubility increases down the group. Easy. Again, so number of cation, number of anion, both are 1, 1. In all other cases, solubility decreases down the group. So who is more soluble? That one is more soluble. In the above one, solubility increases down the group because lithium is for second period element, cesium comes below. In all other cases, solubility decreases down the group. So for alkaline earth metal, it is decreasing. Easy. Now, sir, hydroxide, those 5 ions always increases. Do not look at the cation. This is the way you will find number of questions. Sir, again hydroxide, do not look down the group. Hydroxide increases. Sir, sulfide increases. Sir, nitrate, nitrate was not among that 5. Now, go to cation. Sir, cation is less. So cation equal or cation less? I said when number of cation is greater in all other cases. So here cation is less. So what should be the answer? It should decrease. So it should decrease down the group. Now again, number of cations are 2 by Na plus and H plus. Na plus and H plus 2 cations, carbonate 1 anion. Not the charge, their sankhya, their number. K plus H plus. So bicarbonate salts has 2 cations and 1 anion. So because number of cation is greater, so solubility increases down the group. Bingo. Oxide, sir, for anions, if it is oxide, solubility always increases down the group. I hope you got this point, but life is not that easy always. There are some exceptions. What are those? Just these four, and whatever exceptions also I'm giving, they are just direct questions. You will find number of questions because I have to complete whole lot of chemical bonding, including hydrogen s block basics, which I have promised. So that's why I'm keeping PYQs limited and included all those questions in my theory. So this theory you have to directly go by heart, and it will be helping you like anything in your JEE. Moving ahead. Certain exceptions. Sir, first apply what we know. Then we'll mark and learn those exceptions. Now, sir, NaI, LaI, okay, sir. This is iodide. Iodide was not in those 5 ions, so solubility should not increase, it should decrease down the group. So decrease, okay, decrease. And this is your answer also, sir. But you said it's an exception. Look at the first two. I guess you can very well see this has been replaced. Lithium lithium, sodium should come. So there is a switch between the position of lithium iodide and sodium iodide. This is as per the value. See, initially I told you which salt is more soluble and which salt is less soluble is decided by the value of the lattice and hydration enthalpy. But we do not have to learn their value of hydration enthalpy. But for some, the trend in nature is sometimes not followed. So for lithium and sodium iodide, it is replaced. So this is an exception which we have to learn, else it was following the trend. Barring these two, it was following the trend. Now, coming to alkaline, I'll discuss these two later, then 3 for first. Now, coming to these alkaline earth metals. Sir, it is fluoride. Fluoride was in the case, solubility increases down the group. Fluoride was this case. Fluoride was this case. Again, oxide, sulfide, fluoride, oxalate, hydroxide. Always solubility increases. Okay. So, fluorides. Sir, solubility should increase. Okay, increasing. Okay, I'm sorry. So, increasing. Okay, sir. Sir, what is the exception? Just check what I've done. Beryllium. What is alkaline earth metal? Beta, mange, car, scooter, bap. So, everything are in their exact position except one. Except whom? Except this beryllium fluoride. If you instead it has to be there over here, but instead of having the least, it is having the highest value of solubility. I'll explain you why, but first let us see the trend, the exception in the trend. Now this is a carbonate salt. For carbonate also solubility increases down the group, remember? So increases. So if it is following the trend, how it is an exception? Again check. Beta, beryllium, mange, car, scooter, bap in their respective periodic trend, what we have learned, but this is keep giving us an exception. So again, we have to learn this. No, logic also, you know. What is the logic? Sir, beryllium cation is a second period element. Size is very, very small. So if size is very small, hydration is not high, it is very, very high. So because hydration is very high, hence its solubility is exceptionally higher than expected. So this is all because of high value of phi. And why it is high? Because size of Be plus 2 is very, very, very small. So instead of having the lowest solubility, it has the highest, but it finds its limitation only here. Now, discussing about this is many a times asked. Discussing about the chlorides. So go to your logic first. Sir, it's a chloride. So solubility it is not among that 5 ion. So although cation is also not greater. So it should not decrease. It should not increase. It should decrease. The second one, okay, decrease. So decreasing. Okay, so decrease. Down the group, it should decrease. Okay, decreasing. But actually, it decreases till potassium only. After potassium, it increases. So what will this picture? Why I have written or also, because this picture do not give you the exact order. For example, this is less, but till whom, as compared to whom it is less. So I'm giving you another trend over here, that LiCl is highest, followed by CSCl, followed by RbCl, and then NaCl. So KCl being the lowest soluble alkaline earth metal, alkali metal chlorides. So this is a exception which you should keep in mind. Moving ahead. So next application becomes the order of melting point. Now many of us will have this question, sir. We have already known that if ionic character is more, so melting and boiling point will be high. But my friends, things are not that easy for JEE. I mean, the only point of difference is because one of the chapter has been removed from NCERT, that is solid state. So, what state of matter we actually melt? Sir, we melt a solid. And because the solid itself has some different chemistry, the lattice structure of solid is different for different species. So, you cannot generalize by just knowing one rule of the percentage covalent and ionic character, that is Fajan's rule. So certain exceptions for melting point are there, but can those exceptions be dealt with some logic? Yes, definitely. So as of now, with the applications which we know, what is our final conclusive deal? What is the conclusion is, if percentage covalent character is less, percentage ionic character will be more. And if percentage ionic character will be more, then your melting point will be high. So what I'm doing over here is, whatever basic you know, apply that basic. That phi is our polarization power. So if polarization power is high, covalent character will be high. If covalent character is high, ionic character will be less. If ionic character is less, then melting point will be less. You can very well do this, and do this for all of the compounds except for alkali metal compounds and except for oxides and fluorides, because their solid crystal structure geometry is such that you have to look into their lattice. Now I'm saying they are exception, but to the exception also I'm giving a logic. And the logic is, remember, while doing salts of polyatomic anions and of monoatomic anions, we were giving some criteria for deciding for the dominant factor. So dominant factor is definitely Fajan's rule, because if you are talking of melting point, sir, even I said that whatever properties of ionic compounds are there, you apply that Fajan's rule. So apply that Fajan rule. It will give you your answer. But for alkali metal compounds and for fluorides and oxides, you have to take their lattice enthalpy as the dominant factor. So you will definitely see the charge upon size ratio of the ions, but that will be affecting to their delta H lattice. So if lattice is strong, melting point will be high. So if lattice is strong, charge upon size, obviously for lattice also you only see charge upon size of the ions. But in that case, if lattice is strong, then melting point will be correspondingly high. Now, I mean, this is also just a logic. So let us do some examples for that. Now, for example, order of melting point is our question. So this is oxide, fluoride. Sir, for oxides and fluorides, lattice will give us the answer. So a strong lattice will have a strong melting point. What decides first? Sir, first compare charge. Who has higher charge? Sir, oxygen, because here 2 into 2 is charge is 4, here charge is 1. So obviously charge dominates and it will have a stronger lattice and hence higher melting point. Easy. What about, sir, again charge is deciding, because this is 3 into 3 9, aluminium has plus 3 charge, this is plus 2, so more charge, more lattice, therefore more melting point. So again easy. What about them? Sir, they are oxides. Sir, oxides. So who will decide? Lattice. Charge is same for all. So if charge is same, we'll go with size. Who has the smallest size? Lithium has the smallest size. So a higher lattice as in high melting point. Easy. I mean, common sense is definitely the same. Moving ahead. Now, sir, here charge is only different. Now, but sir, this is fluoride oxide, this is nitride, this is carbide. You can very well apply the same logic of, because fluorides and oxides are there. So this will give you a trend that because for them you are seeing the charge. So definitely look at the charge also, because charge is 9, 3, 3, 4, 4. So charge again decides and lattice again decides. So stronger lattice will have a stronger melting point. Just simple as that. Now, what about them? Sir, they are halides, but halides as in chloride, bromide, iodide, not fluoride. So for all other, what we do? Apply Fajan's rule. So halides are same. So it will be decided by the cations, because cation are the point of difference. If the cation charge is high, the polarization power of cation is high for aluminium. So if polarization power is high, covalent character is high. If covalent character is high, then ionic character is less. Ionic character less, then less melting point. So among these halides, that is chlorides, bromides, and iodides, sodium halide will have a higher melting point just by applying the Fajan's rule. Now, sir, they are also okay. This is not, we are not comparing fluorides, fluoride, chloride, bromide, iodide. So halogen are changing and metal are same. What is the metal? Group 2. It is an alkaline earth metal. So we apply that lattice for alkali metals. For all other, apply Fajan's rule. What is the point of difference? And metal are same. So anion will decide. So applying Fajan's rule, a larger anion has a higher covalent nature. So who is the largest anion? Iodine, I minus. More is the size of anion, more is the covalent nature. So more is the covalent nature, so less will be the ionic nature. And if less is the ionic nature, less will be its melting point. So fluorides again will have the highest alkali group 2 metal, alkaline earth metal fluorides will have high melting point, and alkaline earth metal iodides will have the least melting point. I guess this is quite clear for you. Now, just like life is not so simple. So although for JEE mains I'm suggesting you can leave this exception because they are actually meant for good questions. Mains also ask such questions because again I'm saying I've included all the S block hydrogen concepts also in this side of chemical bonding, because as promised I'll be giving you chemical bonding in such a way that you do not have to read those chapters now. So there are some exceptions, but the exception we have already dealt in the previous slides. Why? Whatever trend we know, follow that. Okay, sir, we'll follow that. But when, what is the anomaly that we find and we face? Sir, anomaly is with when, suppose you are deciding by lattice, but if a cation is very, very, very small, so its polarization will be very, very, very high. So its polarization will start dominating and hampering that ionic compound by making it covalent to much extent. And this anomaly generally takes place with whom? With small size cations. Small size cations as in definitely group 2 cations, but sometimes for sodium also you will see. How? Let us check. Now, the yellow portion, which is actually the exception, which is actually a factual data for us, if you just remove, if you do not see that, and you just go with the trend what we have seen. So what are we comparing over here? Melting point of whom? They're of okay, they are all fluorides. So remember what we have done for fluorides. So for fluorides we know lattice will decide. So who will have the higher lattice will be having high melting point. So small b the cation, because charge is same for alkali metals. So small b the cation, so higher will be its lattice, delta H lattice. So if delta H lattice is high, melting point is high. So who will have the highest melting point? The smallest one. And it will then go on decreasing. But what is the exception? Lithium. I told you, just leave this block. Lithium should have been placed at the top, but instead it is placed in between. Why? Because again, in fact, it should have the highest lattice, but because lithium is very small, so covalent character will start dominating. And what covalent character compel you to be? It compel you to be a covalent compound. And because if I'm forced to have some covalent nature, then my ionic nature will decrease, and if my ionic nature will decrease, my melting point will also decrease. So it starts decreasing, but it loses battle with the sodium and potassium salts. With rubidium and cesium salts, it still win. So this is a actual real-time fact which you can leave also, but I'm giving you this data now. What about other halides? Other halides as in, because in case of alkali metal halides, we have done for fluoride, chloride, bromide, you can again go by logic for chlorides and bromides. Sir, we have said that for fluorides and oxides and alkali metals, these are alkali metals only. These are, no matter you are whatever salt, but you are compound of alkali metal. So for alkali metal also, we will always consider their lattice. So charge is same. So because cation with smallest size will have the stronger lattice and hence will have the highest melting point. So what we are expecting our order to be? It should decrease. So lithium should have the highest, but again, because of the same reason, because of the high polarization power of small lithium cation, it loses the battle, and in this case, it loses the battle from all. So this is a factual thing which you should have to remember. But again, you can leave this exception if not, if that is hurting you a lot. If you are just starting for chemical bonding, you can leave such exceptions. Now, what about iodides? The same pattern is followed because we are talking of alkali metals, but now there is anomaly between the sodium and potassium salts also. They are also interchanged. That's why I placed that block over there. So their position are also interchanged, and criteria is just the same, that it should decrease down the group. Lithium is again over here, but in case of iodides, these two have also switched to their position. This is the exact order of their melting point. Now, some exceptions of alkaline earth metal for melting point. Okay, for alkaline earth metal, what we have, sir, because it's a oxide and it's a fluoride, although it's an alkaline earth metal, but for oxides and fluorides, we always go by their lattice enthalpy. So who will have a higher lattice? Charge is same. So if charge is same, who will decide? Smaller size will have high lattice will have high melting point. So smallest cation will form a higher lattice and high melting point. So down the group, again it should decrease. Again the anomaly. Now the second period, the smallest element in case of alkaline earth metal is beryllium. By the way, beryllium oxide is not at all even alkaline. It is amphoteric, so beryllium is not even termed as alkaline earth metal. It is just a group 2 metal, but not regarded as alkaline earth metal. And moreover, because of its small size, it loses the battle, but again comes in the third position, just like lithium did in case of fluorides. Now, what about the fluorides? Again, this loses the battle, came last, and first and second are also interchanged. So this is again the same order. So although this is an exception, but still I'm giving you a trend for all those students who want to learn one step ahead. Obviously, valid for advanced, valid for very good question in mains, but for all those people who are just doing chemical bonding as of now, they can leave these exceptions. Moving ahead. Talking about the last, finally ending this Fajan's rule, talking about the last application of Fajan's rule. The last application is color. Now, this is again, this is again a generalized thing that I'm telling you. You cannot grab my neck and tell me, sir, you gave this rule and it is, for most of the compounds, it will be followed. By applying Fajan's rule, you can also suggest that whether that compound will be colored or not, because generally ionic compounds are colorless, covalent compounds are colored. So if through Fajan's rule an ionic compound is attaining covalent character, it will have a tendency to show colors also. For example, if I'm asking you to tell me the covalent order of these compounds, sir, apply Fajan's rule. Metal is same. Larger an ion will be more covalent. So who will be more covalent? Iodide. Who will be more covalent? Iodide. Who will be more covalent? Iodide. Who will be more covalent among Iodine and chloride, iodide. So more covalent will have a higher tendency to show color. Now, these colors will play a very, very important role when you deal with salt analysis. So, salt analysis chapter, you have to read them only. So, I'm introducing and coupling it with Fajan's rule also. So, as mentioned by the colors, actually, these all chlorides are white in color, and these two, lead and silver iodide, are yellow in color. Mercuric iodide is Hgi2 is red in color, while mercurous iodide, which is Hg2I2, is green in color. Moving ahead. So moving forward, let us discuss the phenomena of resonance, because we very well know how to draw the Lewis structure of molecules. Now, for various molecules, we will see that one Lewis structure will not be sufficient to signify all the property of that particular molecule. Why? Because generally, whenever a molecule contains pi cloud, also pi cloud has a tendency to delocalize. So actually, whenever there is delocalization of pi electron cloud, more than one structure is required to complete signify all of its property. So whatever the structures we make, those structures are called resonating or canonical structures. This phenomena is called resonance and is given by Heisenberg and was developed by Pauling and Ingold. Although you can forget about this name, but definitely the phenomena of resonance will be asked to you in JEE. One point you always have to remember is number of resonating structures. As the number of resonating structures or the contributing structures or the canonical structure increases, the stability of that particular molecule having that many number of resonating structure is always increased. Now, let me give you an example. We can also calculate bond order, but first let me give you an example. For example, let's say I have to draw the structure of carbonate ion. So one structure of carbonate ion is not possible to completely understand all the properties of that carbonate ion. Why? First, let us try and draw that structure of carbonate ion. It has one carbon and three oxygen. We very well can see that. Now, because we know carbon has 4 electrons in its outermost shell and second period octet, we will definitely complete. So let us say we made this double bond. Okay. Sir, octet of carbon is complete, octet of this oxygen is complete, but this oxygen has 6 electrons, so we have to, because I have to give 2 minus also, so I'll give 1 extra electron to this oxygen. So giving 1 will make a valence electron of oxygen as 7, and because it is forming 1 bond, so octet is complete. So this oxygen will also gain that minus 1 charge. So this is structure of CO3 2 minus. But most of you must be thinking, sir, what oxygen? This oxygen is real brother or blood relationship of this carbon? No. So you can draw double bond here also, then these two will attain that extra minus, and this double bond can go here also. So what we are doing is we are delocalizing the pi cloud coming this, there, and there. So in order to draw and know all the properties of carbonate ion, one structure is not possible, because through our basic we know, if we just look at one structure, and if I'll ask you what is the bond length of all these three C bond O, so we very well know as bond order increases, bond length decreases. But experimentally, when it was observed and checked, it was found that all the bond length of C bond are equal. So one structure will not help you with that property. But these resonating structures do not exist in nature. They help you to predict the average resonance hybrid, and this resonance hybrid is the actual structure in which the molecule actually exists in nature. Sir, how can these three resonating structures can be used to draw that resonance hybrid? Very simple. Sometimes you are double, sometimes you are double, sometimes you are double. Single bond you all are having in all these three structures. So sometimes you are double, sometimes you are double, sometimes you are double. What this dotted line is telling us? This dotted line is telling us that there is a presence of, this is partial double bond character. So this partial double bond character is telling us that bond order between C bond O is not 1. It is more than 1. But how much more? So that's why you have to know how to calculate the bond order, because all the properties, what is the property of this compound? That all these bond length are equal. Let's say this bond length is X. So this is also X and this is also X. So why the bond length are similar? Because bond order are equal. And what is the bond order of the C bond O? So bond order can be calculated as, you just pick any C bond O from any of the three structures. Let's say we are picking this top one. So what is the bond order in first resonating structure? 1. What is the bond order of this particular C bond only in this resonating structure? 2. What is the bond order in third resonating structure? 1. How many resonating structures we have? 3. So what will be the value? It is 4 by 3. So bond order will be 1.33. So because bond order is same, so all bond length will be same, and this phenomena is known as resonance. Now, how questions are asked? These bond orders are also asked to you in the question, and some other type of question. Like for example, if I have to comment about the bond order of N bond O in nitrate and nitrite ion. Now let us try and make that structure. Nitrate ion is NO3 minus. Sir, how we are supposed to draw its Lewis structure? Nitrogen. Let's say how many electrons nitrogen has? 5. It will make 3 bonds. Octet of nitrogen is complete. Octet of this oxygen is complete. Octet of this oxygen is not complete. We'll give it an extra minus charge, because minus, this is nitrate and minus has to be given. Now, what about the third oxygen? Third oxygen can be easily coordinated. But sir, coordinate bond is similar to that of a covalent bond. We have already discussed that. Then if you wish to do that, then make it a covalent bond. But whenever we replace a coordinate bond with a covalent bond, plus goes to the donor atom, minus goes to the acceptor atom. So overall charge is -1 only. So this is the first resonating structure. Why I'm saying first resonating structure? Because you can see over here also, this oxygen can be double, so this can also be double. So the second resonating structure will be, this can also be double, so this will be O minus. What about third resonating structure? O minus, O minus. How many resonating structures we again have? 3. Does N bond O exist in one of these forms? No. NO exists as the average resonance hybrid. So what will be the average resonance hybrid? Every nitrogen is definitely having one single bond. Overall, -1 is carried by the whole molecule. So my overall charges I have placed at the top. Now, sometimes this is double, sometimes this is double, sometimes this is double. So what will be the bond order? Bond order will be equal to, what is the bond order? 2 plus 1 plus 1. So that is 4 divided by number of resonance structure 3. So this is also 1.33. Now, what about nitrite ion, sir? Nitrite ion is NO2 minus. Okay, so let us try and draw the resonating structure of nitrite ion. N, double bond O, single bond O, and a minus. Octet of everybody is complete. So what resonating structure I can draw? Sir, one more. This can be single. So how many resonating structures I have drawn? 2. Does both these bond length are different? How can you predict that? By drawing its average resonance hybrid. So let us draw that average resonance hybrid for nitrite ion also. So what it will be? Nitrogen, single bond is always there. Sometimes you are double, sometimes you are double. Overall molecule is having -1 charge. What is bond order over here? The N bond O bond order. this is 1 plus 2. So 2 plus 1 is 3 by 2 as in 1.5. Simple. Now, if somebody is asking you, let's say this bond length is X and this bond length is Y. So what is the relationship between bond length of N bond O? Both atoms are same, but bond length will not be same because bond order is different. So who has a higher bond order? Nitrite ion. So X value of X is more than that of, because bond order is higher, so bond length, okay, I'm sorry, because bond order is higher, so bond length will be less, because bond order is inversely proportional to bond length. So these are the type of questions which you will get. Now, if somebody is asking you which is more stable, the nitrite ion or the nitrate ion, more be the number of resonating structures, more stable is the resonance hybrid. So nitrate ion has 3 resonating structure, and hence among nitrite and nitrate ion is more stable. So I'm saying this is more stable with respect to nitrite ion. Why? Because of the number of resonating structures. Now, one more example, a very good indeed, bisulfate ion. Now, I'm asking you, you tell me charge per oxygen atom, that oxygen atom which is having charge. So charge per oxygen atom is how much? And obviously the bond order of S bond O, but that O which is having a minus sign. So first let us draw the bisulfate ion. What structure, loose structure it will have? Sulfur, okay, 1 OH. Now we very well know second period elements do not have empty d orbitals, but expansion of octet can always take place. So this is O minus, because this is H bisulfate is HSO4 minus. So minus 1 it has to carry. So minus 1 I've given. How many more atoms I'm having? 2 oxygen atoms. How many electrons sulfur has in its outermost shell? So 6. So how many bonds it can make? 6, because expansion of octet can always take place. Drawn. Now, sir, you have drawn a double bond to these two. It can delocalize also. Okay, then do that. How to do that? If you just check, what I'm trying to do over here is double bond. Okay, this has given us no profit. So this is O minus and this is double bond O. And over here, okay, this has not given us any profit. The draw. So this was O minus, this is O minus. So who is remaining to get that single bond? This one. So how many resonating structures I'm having? 3. So if I'm having these 3 resonating structures, you tell me what's first, tell me the charge per oxygen atom. Charge is carried by how many oxygen atoms? Sir, 1, 2, 3. Sometimes this is carrying, sometimes this one is carrying, sometimes this one is carrying. So minus 1 is carried by 3 oxygen atoms. So charge per oxygen atom will be minus 1 by 3. That is minus 0.33. Now, if I ask you the bond order of these O minuses, the S bond O minus, concentrate on any one. Let's say on this one, 2 plus 1 plus 2, because number of bond order of a particular bond, and focus your attention to that particular bond only in all the resonating structures. So bond order is 2 plus 1 plus 2. So 2 plus 1 is 3 plus 2 is 5. So this will be equal to 5 by number of resonating structure is 3. So what will be your bond order? It will be equal to 1.67. So moving ahead, just check this. So quickly moving to the most loved portion from chemical bonding and whole of inorganic chemistry by especially JEE mains, that is VSEPR theory. It is just a theory which will help you to account the shape of all the covalent molecules largely. So it is valence shell electron pair repulsion theory, which is obviously used to predict the shape of molecules. And whenever combining atom approach the central atom, the whole of the molecule will acquire such a shape in the universe, in the three-dimensional orientation of the universe, in which the repulsion forces that it will be experienced must be minimum. So this, the main postulate of VSEPR theory is, when the central atom is approached by the combining atoms, the valence shell of the central atom gets divided basically into two parts. We have already discussed. One, those electrons which are used for sharing are called bond pair electrons, and those set of electrons of the central atom which are remained behind are called lone pair electrons. So VSEPR theory helps us with a proposal, with a postulate which says that repulsion between lone pair is the maximum, followed by lone pair bond pair electrons, and the last and the least repulsion forces is dominant among the bond pair electrons. Now remember, although the overlapping and the actual fundamentals of hybridization we will be covering in the second part of bonding, because as promised, I have included all the specific basics of the block studies with the chemical bonding only. And because this will be I don't want to make a large a video which should have a higher duration. Therefore, in the beginning also I mentioned that I have divided this bonding into two parts. This bonding one that we'll be finishing, so we'll be finishing with VSEPR theory, and whatever theory, the VBT, the hybridization, the molecular orbital theory, the intermolecular forces of attraction, that is hydrogen bonding, van der Waals forces, and their fundamentals, will be discussing in the bonding 2 part of our next video. So coming back to VSEPR theory. So whenever central atom is approached by combining atoms, as of now with VSEPR theory only, because this is loved by JEE, I wish and I want you to understand that hybridization state. What is hybridization? Whenever central atom is approached by combining atom, the orbital overlap will take place. And hybridization just says that whenever you are welcoming any guest at your place, you modify your rooms. So similarly, central atom modifies its orbital, and those modified orbitals are of equal energy, equal shape, and equivalent orbitals are formed. So to those modified equivalent orbitals of the central atom, we refer them as hybridized orbital. So who all orbitals undergo hybridization? The one which is having lone pair, and the one which is forming the first bond, the sigma bond. Because if I'm considering only about the geometry of the molecule, so I need to find the position of central atom and the combining nucleuses with the central atom. Suppose a central atom has approached, it has definitely formed a sigma bond. Post the formation of sigma bond, it may form pi bonds, but for our bond pair consideration, we will only, for VSEPR theory and for hybridization, we will only account the, for bond pair electrons, we will only account the sigma bonds. The pi bonds we will not account for calculation of number of bond pair electrons. Now, so these repulsive forces we know, the maximum is lone pair repulsion, followed by lone pair bond pair, and the minimum is bond pair repulsion. Now, moving ahead, again, as I said, hybridization state you should know, and it's a very small trick. It's a very small concept. The concept says that you calculate steric number. So what is steric number? Steric is the crowding around the central atom, is represented scientifically, technically, by the word steric, as in three-dimensional hindrance with a central atom is facing because of approach of other nucleuses. So steric number, which is Sn for us, is nothing but summation of bond pair plus lone pair. As already said, for bond pair we will only count the number of sigma bonds formed by the central atom. So let's say if the steric number for any central atom comes out to be 2, so hybridization will be how many high orbitals you will be requiring to modify 2. So hybridization state of the central atom will be sp. If it is 3, then sp2, because s has 1 orbital, p has 3, so sp2 So till 3, till steric number 4, it is sp3. Although in complexes, you will see that inner shell also participates in hybridization. So sometimes in complexes mostly, you will find this dsp2 hybridization as well. But these pink color hybridizations, you will mostly see in coordination complexes. So we'll be discussing that also in the bonding second part and in coordination complexes in organic. If steric number is 5, we will now focus on sp3d. If steric number is 6, the hybridization is sp3d2 because I'll be requiring 6 orbitals. So how many hybridized orbitals will be formed? 6 hybridized orbitals will be formed with all equal shape, equal energy, and what will be the name of those hybridized orbitals? sp3d2. Inertial orbitals can also be undergoing hybridization, but they basically find their existence, this inertial hybridized orbital find their existence in case of coordination and complex compounds. So quickly moving to the most loved part of application of valence shell electron pair repulsion theory, which is the shape of molecules. So first we'll be discussing about the shape of the symmetrical molecules. Now what are symmetrical molecules? Generally, symmetrical molecules are those where the central atom is not having any lone pair. So this is basically the cases when lone pair on central atom is 0. So what are these symmetrical shapes? The very first one, AB2 type of molecule. Suppose I'm a central atom, let's say hydrogen. If I'm attached with only one atom, let's say chlorine, so what will be the in order to join two line, it will be a straight line. So shape of a diatomic molecule will always be linear. So I'm starting with the when bond pair 2. So if I'm the central atom, one atom has come from that side, one atom has come from that side. So what will be my shape? I will only be having bond pair repulsion, because I'm for symmetrical molecules, the central atom is not having any lone pair. So first we are starting with the simplest case. So this type of molecule we will now refer as AB2 type of molecule. So what is the shape of those combining atoms with respect to me? So this molecule will be definitely linear. So the shape will be like this: central atom linearly combining with the combining atom. So there are two bond pair, lone pair is 0, so steric number is 2. So shape is linear. What can you comment about the bond angle? I guess it is quite easy to say this bond angle is 180 degrees. Sir, some examples obviously, like BeCl2, beryllium has 2 electrons, will form 2 bonds. CO2, carbon has 4 electrons in its outermost shell. 2 electrons will be used for the bond formation with oxygen and 2 again for the another oxygen, but we only count the sigma bond. So 1 sigma bond and 2 sigma bond. Pi bond we do not take into consideration for calculation of bond pair, as already said. So bond pair of CO2 will also be 2. There will be no lone pair, so obviously symmetrical shape, and shape of CO2 will therefore also be linear with bond angle 180 degree. Now the next type of molecule is AB3, when bond pair are 3. For example, this, the central atom is combining with 3 different, maybe same or maybe different, 3 other nucleuses. Now in order to have the minimum bond pair repulsion, what orientation they attain in the 3-dimensional space? They become a trigonal planar molecule. They becomes a trigonal planar molecule with bond angle of, obviously you can definitely see it is 120 degree. Some examples like BCl3, like SO3, although sulfur, come over here, sulfur, double bond O, double bond O, double bond O. Sulfur has 6 electrons in its valence shell. We only have to calculate, if approach is to be determined, we only have to see the sigma bonds. Yes, pi bond we are seeing, but just in order to check that whether lone pair of electrons are remaining or not. For bond pair calculation, I'm again and again repeating, we will only count the number of sigma bonds. So shape of SO3 will be trigonal planar. Now AB4 type of molecules. Now when central atom is approached by 4 combining atoms, the shape that the central atom acquires with respect to combining atom is called tetrahedral. This is a tetrahedral geometry where 3 atoms forms a base, a triangular base, and this is a tetrahedron. All bond angles are same, and hence it is also a symmetrical molecule, and these bond angles are nothing but they are equal to 109 degree 28 minutes. It is a tetrahedral structure. Who all molecules exist as a tetrahedron? Methane, XeO4. How can you predict this XeO4? Sir, very simple. Xe, double bond O, double bond O, double bond O, double bond O. What I told you, that in the base they forms a triangle, and this triangle is existing as a tetrahedron. I'm sorry, this is existing as a tetrahedron with the not I mean, you must have seen the picture. So this is a perfect tetrahedron which you can assume. Now xenon has how many electrons in its valence shell? 8. But since how many sigma bonds it is forming? 4 only. But the other electron is used for pi bond formation, so lone pair is not present. So because it is surrounded, xenon is surrounded by 4 oxygen atom with no lone pair, so this forms a shape of tetrahedron. Some other examples: ammonium ion. Ammonium ion, nitrogen has how many electrons in its valence shell? 5. If nitrogen loses 1 electron, how many is left? 4. So this is nitrogen plus, and if it is getting attached by 4 hydrogen atom, this is nothing but a tetrahedron of ammonium cation. Now a very famous example, it was asked by JEE Advance, this one, SNF3. Can you tell me what is the shape of SNF3? Sir, simple. SN, nitrogen is a second period element, so its octet we'll definitely complete. So this is 1 sigma bond. Sulfur has how many electrons in its valence shell? 6. So SnF6. So how many electrons are left for sulfur? Sir, 0. So again it's a case of 0 lone pair. And how many sigma bonds? How many bond pair? 4. So its shape will also be a tetrahedron. Moving ahead, all in a tetrahedron, all bond angles are 109 degree 28 minutes. Although this exact 109 degree 28 minute happens when the combining atom are similar. For example, if you grab my neck and if you'll ask me, then obviously there will be some difference in this bond angle and these bond angles, because bond length will also be different, and so bond angle will corresponding also change a bit. But when we say we are having symmetrical molecules, symmetrical shape, we generally talk of the molecules where combining atoms are similar. And whenever combining atoms are similar, the net dipole. So what is dipole? I'll be just finishing this symmetrical structure and then we'll quickly, that's a very small thing, we'll quickly cover that dipole thing also. Now, if central atom is approached by 5 combining atoms, the shape becomes trigonal bipyramidal. What becomes the bond angle? 3 bonds are placed in a triangular plane, and 2 bonds are upside of the triangle and downside of the triangle. So for example, PCl5, the famous example. So let's say this is a phosphorus. 3 bonds are equatorial, that is lying on the triangular plane, and 2 bonds are axial. So these are axial bonds and these are equatorial bonds. Equatorial bonds, my friends, they are lying at an angle of 120 degree, while the axial bond, my friends, are lying at an angle of 90 degree. So you tell me who will have more repulsion? 90 degree bond electrons are closer, so they'll be repelling more. So because the repulsion is more, so this bond length, the axial bond length, will definitely be greater than the equatorial bond length. Therefore, when you take PCl5 is not very stable. You slightly decompose it, you slightly increase the temperature, it quickly breaks into PCl3 and Cl2. Why? It leaves those 2 chlorine atoms, because those 2 chlorine atoms require very less of bond energy because bond length is high. So bond energy required to break that bond is very less. Therefore, PCl5 easily decomposes to form PCl3 and Cl2, because these these two chlorine atoms which are present axially are not in love with this phosphorus, because the bond length is high. The bond length of equatorial bonds will be larger. It will be more stable. A very, very important point and observation as well. Now, the last symmetrical structure, why I'm saying last, because generally when a central atom is approached by combining atoms, in nature we have observed is when a central atom is approached by 6 atoms, the molecule becomes very stable. And post 6 combining atoms, let's say if 7 is coming, they also create so much of hindrance, so much of crowding around the central atom, that those molecules also break. So because those molecules easily break, so they generally do not exist in nature. So what is the covalency? How many combining atoms we generally see around a central atom? It can maximum go to a value of 6. Although very, very, very rare cases, JEE do not love it. JEE mains do not love it at all. So where we are stopping is till bond pair, till steric number of 6, because after 6 crowding increases to such a large extent that those molecules are not at all stable in nature. They quickly dissociate. So if they dissociate, they do not exist. They will not have some important properties also to play in our daily life, and hence not loved by NCERT, not loved by JEE. So we are stopping till case of AB6 type of molecule. So AB6 type of molecules are, again, it is simple. When there were 5, you have taken 3 in a plane, 1 up, 1 down. So there are 6. So we'll take 4 in a plane, 1 up, 1 down. So this shape will be square bipyramidal. But instead of square bipyramidal, what is the famous word is an octahedron. Why? Just look into this picture. This is a square bipyramidal structure only, but in scientific world, this square bipyramidal is more commonly termed as an octahedron, because you can definitely see it has 8 as an octa triangular faces. One triangular face, this one, this is the second one, this will be the third one, and this is the fourth one. So if I'm a square, I'll be having 4 triangular faces at the top, and similarly 4 triangular faces at the bottom. So how many triangular faces I'm having? 8. So that's why what is the most commonly used word for this type of structure? Not square bipyramidal, although it is not technically wrong, but NCERT uses the word, scientific community uses the word octahedron. Now some example of an octahedron, very simple. SF6. Sulfur has how many electrons in its valence shell? 6. How many bond it is forming? 6. So 6 bond pair, no lone pair. So bond pair is 6, lone pair is 0, steric number is 6, and shape will become octahedron. Obviously, we can see all bonds are mutually perpendicular to each other. So all bond angles are simply 90 degree. There is no axial or equatorial bonds over here. Why? Because all are at equal bond angles. So they all will be having and experiencing the similar repulsive forces. So all these bond lengths are same, and hence SF6 is a very, very, very stable molecule. In fact, these days in the circuit breakers that you find around in the large substations, the circuit breaker also uses this SF6 gas as an inert atmosphere creating gas, because this molecule is very stable, unlike the PCl5 where what we have discussed, because the bond lengths were unequal, because atoms were experiencing different forces of attraction. So these are all inorganic facts which are loved by JEE, and you should know also. Now, what I said is symmetrical shapes are non-polar in nature. So first and why they are non-polar? Because their mu net is 0. What is mu net? So first let me tell you about what is this mu. Nothing. It is, in physics you must have seen, whenever two equal and opposite charges are separated by a distance, this constitutes a system, and this system is known as a dipole. This dipole has a capacity to attract and repel charges around it. So obviously you have to quantify the magnitude. So the quantification of the force that this dipole exerts to the outside world is calculated by the factor called dipole moment, which is represented as mu. Its magnitude is charge into distance between charges, and its direction, it directs its force of electric field from positive to negative, because it's a vector quantity. So magnitude is q into d, and direction is from positive to negative. Now, once we know this, one more thing, what is its unit? Its unit is, although you can take the SI unit of charge and distance, which is meter, so coulomb into meter, but its unit is generally referred as debye by the name of the scientist who has quantified this formula for us. So 1 debye is nothing but it is equal to 10 raised to power minus 18 ESU into centimeter, because JEE has many times asked this also. CGS unit of charge is electrostatic unit ESU, and if using CGS system of charge, then generally it comes with the distance in centimeters. So what is 1 ESU in terms of the SI unit of charge, that is coulomb? 1 ESU is equal to 3.335 into 10 raised to power minus 10 coulomb. So 1 debye equals this into 10 raised to power minus 30 coulomb into meter in SI unit. What is the application of this dipole moment? Sir, in periodic table we have seen how to calculate percentage ionic character, but with dipole moment also you can calculate percentage ionic character. How? You will definitely calculate for any molecule, you can calculate the mu. So whatever mu you calculated, that will go to the denominator, but what you have calculated will be shown by nature also, sir, maybe or maybe not. So what mu you have calculated, the calculated one, if the actual observed mu is same, then your ionic character is 100%, because that dipole is perfectly acting as a ion, because charges must have been in such high magnitude. But if it is not so, then percentage ionic character will obviously decrease. So covalent molecules are polar in nature, but how much polarity they will be attaining will be decided by this percentage ionic character. So more I will actually, mu observed is the actual dipole moment that polar covalent molecule is going to show. Like for example, if I'm having HCl, this was having a delta negative and this is having a delta positive. Now this is not complete -1 and complete +1. So how will you technically calculate how much of this magnitude of charges? By knowing the value of the dipole moment it practically gives in nature. By telling you this, loved by JEE, a question in JEE mains came on this topic only. The question says a diatomic molecule has a dipole moment of this. So this is the mu. This is the mu observed, the actual mu that is given to you. And if bond length is 1 angstrom, the fractional charge, now it is asking you the fractional charge. By when you apply theory, for example, let's say if I take HCl, when I write delta minus delta plus while calculating, I have to put this charge. So this is complete -1 or complete +1? No. What is the partial charge, sir? I cannot know. So how can you know? By observing its dipole moment. So what is the mu observed? So mu observed will be equal to the Q actual, which we do not know. We will calculate by observing this observed mu, which question has supplied to you, into distance between charge. Now this is now just basic physics of yours. You have to go by basic of unit dimension. So what is mu observed, sir? 1.2 debye. What is 1 debye? Although we know it is 3.335, but question is telling you, you just take 10 raised to power minus 18. So this becomes in ESU, electrostatic unit. Now what is Q? Now whatever Q will be, you will be getting in ESU only, because question is also asking the fraction of charge in ESU only. So this Q will be coming in electrostatic unit only into. Now distance between charges, the bond length is given, that is 1 angstrom, but this 1 angstrom bond length has to be converted into ESU into centimeters. So 1 angstrom is how many centimeter? Because now we are going into CGS unit. So 1 ESU is how many centimeter? 10 raised to power minus 8 centimeters, because now I'm centimeter ESU. So debye is also centimeter ESU. So now unit is same. So this -8 will be gone. So this will become 10 raised to power minus 10. So your answer is simple. 10 raised to power minus 10. The fill in the blank you have to fill. Your answer is 1.2. Simple. But JEE asked these questions. That's why I've told you in between. Now coming again to my VSEPR theory. We have discussed about dipole moment. It's a vector quantity. So let us go to the symmetrical shapes. For example, any symmetrical shape, this let's say I have CO2. So one vector will be on that side, one vector will be on that side. So my mu net will be 0. Talking about BCl3, one vector will be acting on this side, this side, this side. So this much physics, I guess you know. One force is, this is force F, let's say value of mu. This is also mu. This is also mu. So how will you resolve the, let's say this is theta. So this is mu cos theta. This side mu cos theta. This side cancelled. Mu sine theta downward. Mu sine theta of this also. Mu sine theta of this also. So this will be 2 mu sine theta. Can you tell me what is this value of theta? Sir, the whole angle is 120 degree. So if this is 90 degree, this will be 30 degree. So what is sine 30? 1 by 2. So what will be the downside to mu or to f? Sine theta, sine 30 is 1 by 2. So this will be cancelled. So mu upside, mu downside. So in all respective cases, if you'll do just the simple physics, what you will find is the mu net will always come out to be 0. And because the molecule is constituted of this is boron, this is chlorine. So they are polar in nature, but the overall molecule, because dipole moment is cancelled out, so the overall molecule becomes non-polar because its net dipole moment is cancelled. So that's why I'm saying this conclusion which I'm giving, that all symmetrical structures are non-polar. All symmetrical structures have mu net equal to 0, and because they're mu net equal to 0, so they becomes non-polar. But the mu actually gets cancelled when charges are also, the value of mu is q into d. So when that q into d are same, when all the combining atoms are similar. If they are dissimilar, then obviously the vector addition will try to cancel out each other, but the magnitude will not be equal. So there will be some value of mu net that will be coming out of that molecule. So this symmetrical shape having non-polar property, they have mu net 0, is only applicable for those molecules which are constituted of similar combining atoms. Moving ahead. Now, rushing and quickly moving, I guess this is quite clear to you, with those type of molecules where lone pair exist in the central atom. The first case, when steric number is 3. Sir, how can steric number be 3? You can apply n number of permutation combinations. So what I'm only discussing those permutation combinations which are highly loved by JEE also, and in nature also they only exist. Now, AB2L as in 2 bond pair, and 1 lone pair. So steric number is still 3. So 2 bond pair, 1 lone pair. 2 bond pair, 1 lone pair. Steric number is 3. So what geometry? Geometry you will always go by the symmetrical shapes. So what geometry you will think of? Say trigonal planar. But over there, one bond pair is replaced by a lone pair. And we know lone pair repulsion is higher. So this lone pair bond pair repulsion is higher. This lone pair bond pair repulsion is higher. So this bond angle theta, which was symmetrically 120 degree, so over here this theta will be lesser than 120 degree. Now this is about the geometry. What about the shape? Sir, when you see the shape, you cannot see the electron. What you can see through spectroscopy also, you can only see the nucleus arrangement with respect to other nucleuses. So this nucleus with respect to other nucleus is giving you what shape? V or bent shape. So shape is V shape, or some people call it V shape or bent. Some examples, obviously, like SO2, 2 bond pair, 1 lone pair. This is, although intermediate, this is called dichlorocarbene. So it is having 2 chlorine, so 2 bond pair, 1 lone pair. Although this is not a very stable species, in organic chemistry you will see that it is a reaction intermediate, but a very famous one. So this is dichlorocarbene. Its shape bent. This angle, I am not sure what it is. I'll do spectroscopy and I'll check, but I can definitely be sure that this will be less than 120 degree. Why? Because VSEPR theory told us lone pair bond pair repulsion is higher. So if it is higher, this bond length will be decreased with respect to the symmetrical bond angle, which was 120 degree in case of geometry of trigonal planar. Again, ozone. So ozone is what shape molecule? Bent, because two bond pair, one lone pair. Moving ahead. Now, when steric number is 4, how can it be 4? Let's say it has 3 bond pair and 1 lone pair. So steric number is still 4. So what geometry you will think of? Tetrahedron. Thought. Replacing one bond pair by lone pair. Replaced. What can you, after seeing this geometry, what can you comment about the bond angle theta? Sir, I do not know what this bond angle will be. But it will be, because of presence of lone pair, it will be definitely lesser than the symmetrical arrangement, which is 109 degree 28 minute. And when you have to comment about the shape, you will not see the lone pair, because shape is always arrangement with respect to combining atoms, combining nucleuses. So what is the shape? The base is a triangle and it forms a pyramid with the central atom. So shape is termed as trigonal pyramidal. For example, ammonia. Over there, I have written bond angle also. It is less than 109 degree 28 minute, but because this is a very famous molecule, so its bond angle is approximately 107 degree. Exact value, I guess it is 106.7 degree. So obviously less than tetrahedral angle. Now, XeO3, 3 bond pair, 1 lone pair. Moving ahead. Now, if steric number is again 4, but with 2 bond pairs and 2 lone pair, so we'll again think of geometry of a tetrahedron, but replacing 2 bond pair by lone pair. So what can I comment about this angle? This angle will definitely be lesser than the symmetrical angle. Easy. When you have to look at the shape, don't see the lone pair. So what arrangement you are seeing? Again a V or bent shape. Some example, water. Obviously this theta is less than 109 degree 28 minute, but this is also less than tetrahedral angle. Ammonia was also less than tetrahedral angle. Do you have to always do experiment? You cannot predict. I'm not saying you tell me the value, but can you tell me if bond angle of ammonia is theta 1 and bond angle of water is theta 2? Let's say this is theta 1 and this is theta 2. Sir, two lone pair of electrons will give more repulsion. So bond pair will come closer to each other. So theta 2 will be lesser. And you can see also it is 104.5 degree. So water and ammonia, famous molecules, so telling that also. Another example, the BrF2 plus, again a JEE advanced question actually. So I have included all the basics, all the examples which you will find there, then in mains question, advanced question. I have taken all of the examples. I'll be discussing few examples at the when we'll be finishing this, but the examples you will definitely have to revise these things very thoroughly. Now, BrF2, sir, how? It is BrF2 plus. How many valence electron? Bromine has 7. So if one gone, so Br plus. So how many remaining? 6. How many bond pair? 2. So fluorine uses 1 electron to form a bond pair. So out of 6, 2 are gone. How many remaining? So 4. So how many lone pair? 2. So 2 lone pair, 2 bond pair. So again shape will be like this. That is, it will also be a bend shaped molecule. Moving ahead. Now, if steric number is 5, and if steric number is 5, first let me tell you this, that if steric number is 5 and you are introducing lone pair, so lone pair can go to any position. You will first think that. Let's say lone pair is how many possibilities of acquiring positions a lone pair has? Sir, axial position or equatorial position, because we are talking of steric number 5. Steric number 5 symmetrical shape is trigonal bipyramidal. So it can either acquire axial position or it can acquire equatorial position, because all 3 equatorial positions are same, both the axial positions are same. Now, if it has acquired axial position, you can clearly see the lone pair is at a bond angle of 90 degree. So it will be giving more repulsion. If repulsion is more, molecule will not be feeling comfortable. So if not feeling comfortable, why the molecule will acquire this? No. So whenever for steric number 5 case, lone pair are there in the central atom, it always acquire equatorial position, because the repulsive forces becomes minimum and the molecule becomes good, stable in nature. So for steric number 5, lone pair always acquire equatorial position. Going to the structures, steric number 5, in nature this permutation is seen. 4 bond pair, 1 lone pair. So doing what? In equatorial position, replacing 1 bond pair by a lone pair. What can you, obviously, sir, the angle was 120 degree and 90 degree, and those axial bonds, if they were at 90 degree, because this lone pair bond pair repulsion is higher, so they'll also at least bend, move apart from lone pair, because repulsion that they are experiencing from bond pair is less, so they'll be more comfortable in moving that side. So that's why I've drawn this tilted sign. So some example, obviously SF4, sulfur has 6 valence electrons, 4 bond pair, 1 lone pair. This shape is termed as seesaw shape. Someone call them arrow shape. Like you can also draw like this, no? So some people call it arrow shape, but mostly in questions you find this shape is termed as seesaw shape, because with geometry you can comment about the angle. So we have said it is not 90 degree, it must be increased. So this bond angle will be decreased. But in order to see shape, we do not see lone pair. So what shape we are seeing? Sir, seesaw. Seesaw. You and kids are playing. Must have seen in the park that seesaw shape. Moving ahead. Stage number 5, with permutation of 3 bond pair and 2 lone pair exist in nature. Very famous examples: IF3, CLF3, bond pair 3, lone pair 2. Shape becomes, lone pair will acquire what position? Equatorial position. So what is this shape? This is T shape. Somebody obviously you will say this is also get bent. So there I have drawn also. This is someone even call it as bent T shape. But NCRT usually write as T shape, but we definitely know this angle will not be 90 degree. This theta will be less than 90 degree, because they'll be experiencing repulsion from the lone pair. Moving ahead. Bond steric number 5 with another permutation combination of 2 bond pair and 3 lone pair. So this is bond pair plus lone pair combination. So 2 bond pair, 3 lone pair, some molecules are formed, definitely yes. XCF2. 2 bond pair, 3 lone pair. Lone pair acquire what position? So lone pair acquires equatorial position. So what can you comment about the angle? Sir, it will experience fluorine will experience repulsion from that side also, this side also. So it will be directly at the perpendicular angle. So here angle is exactly 90 degree, because it is experiencing similar force from this side and similar force from this side. So what this shape is? This shape is exactly a linear shape molecule. A very famous example loved by JEE. Moving ahead. Now, this we have already discussed. Now, steric number 6, sir. Steric number 6, what permutation is seen in nature? 5 plus 1. 5 bond pair, 1 lone pair. So doing what? Go to your symmetrical shape, that is octahedron. Replace 1 bond pair by a lone pair. Example, so BrF5. Example, okay. Now this BrFR, when you are asked about its shape, don't see the lone pair. So this is a square and a pyramid. But obviously you will say, sir, this why it will be a perfect square? I am not saying it will be planar. It will be tilted like a rocking chair. It will be not planar. It will be tilted. Bond angle, I'm not saying it will be 90 degree. Over there I've mentioned also, because lone pair will be, but mostly the shape will be, although it will be tilted to this square. What you will nomenclature? What will you name? So we name it as square pyramidal, this pyramid at the top, although I know this square will be tilted. That's why I'm telling you the angle also. That angle will not be 90 degree, and I'm giving you a fact also. Don't remember that fact, that is for advance. But this angle is less than 90 degree, a common sense, and it is exactly equal to 84.8 degree. So in BrF5, although we say shape is square pyramidal, but no FBrF bond is 90 degree. It is obviously less than 90 degree, because repulsion from lone pair is obviously higher. Now, next combination, 4 plus 2. So now, in the geometry side, geometry is octahedron. But what will be the shape? Replace 2 bond pair by lone pair. Sir, why replacing opposite lone pair? Because lone pair has to be at maximum distance from each other. So what shape you have? Now you have a perfect square, because these bond pair will experience repulsion from upside also and downside also. They'll remain where they are. So it will be a perfect square. So it will be a perfect square. So angle will be perfectly 90 degree. So this angle will be perfectly 90 degree. Example, XCF4, 4 bond pair, 2 lone pairs. Moving ahead, this VSEPR theory, my friends, is going to now I'm coming to questions, because let's wrap up this chemical bonding one and dealing with some questions, and moving ahead. Now, number of species from the following in which central atom uses sp3 hybridized orbital. Okay, sir, so what we have to use? Sp3. So at least you have to give me the hybridization state. Nitrogen, bond pair 3, lone pair 1. Why? Nitrogen has 5 electrons in its outermost shell. So hybridization will be just steric number. I told you steric number is 4. So hybridization is sp3. So this is an answer, because I have to tell that central atom is sp3 hybridized. Yes. Now SO2, sulfur, 2 bond pair, but sulfur will be having these 2 bond pair. So how many lone pair it is left with? 1. So steric number is 3. If steric number 3, hybridization is sp2. So not an answer. Now I'm leaving SiO2. I'll tell you why. Now BeCl2, Be, one Cl, another Cl. Shape is linear. Hybridization is sp. So not an answer, because there is no lone pair. CO2, C, double bond O, double bond O. Bond pair is 2, lone pair is 0. So again hybridization is sp and shape is linear. So not an answer, because hybridization will be, steric number is 2. So hybridization will be sp. Water, this we have recently seen. 2 lone pair, 2 bond pair. So perfect sp3 hybridized. Shape is bent. Yes, an answer. Methane, tetrahedral, classic structure, sp3 hybridized. So yes, an answer. BF3, 3 bond pair, no lone pair, trigonal, planar. So sp2. So not an answer. So now we have 1, 2, 3, but this SiO2 I have left, because as promised, this is actually a common sense of carbon family. Actually, SiO2 in nature exists as a covalent solid, like this. So for covalent solid, it is a network of silicon oxygen, silicon oxygen, silicon oxygen, silicon oxygen. So what formula you get is just like for an ionic solid, like I have told you in case of improper characteristic of ionic compounds, that for them their empirical formula is only existing in nature. For an exact solid, you only get their empirical formula, because they are definitely an arrangement of n number of those atoms. So silicon oxygen, silicon oxygen. So this goes this side also, this side also. So this is a 3D arrangement, a whole very strong network solid of silica is SiO2. So actually, I'm giving you this structure also, because this we have we have drawn thinking in a 2D plane. But we know when when an atom forms 4 bond, silicon has how many electrons in its valence shell? 4. If form 4 bonds, so its shape will be tetrahedral. So giving you that tetrahedral image also. So what will be the hybridization of this silicon? Sir, it is sp3, but it is a fact that involves the common sense of study of carbon family. So because SiO2, silicon also has sp3 hybridization in nature, and therefore this will also be your answer. So how many central atoms are sp3 hybridized for us? So here answer is 4. A very important basic I've discussed. Moving ahead. Now, next question says the hybridization of phosphorus. Again, this is very simple. Phosphorus has how many electrons in its valence shell? 5. So hybridization will be, steric number will be 5, sp3d. So p is x and d is 1. So 3 is x and 1 is y. So y we are we are asked by the question what is value of y. So y is 1. Lone pair of compounds with 1 lone pair of electron on central atom. Again, just do the basic. For practicing also I have just included these. They are all JEE mains question. Now, central atom should have 1 lone pair. The question is asking us. So we have to again draw the shape. Ozone, double bond, coordinate bond. Yes, because these lone pair are utilized to form a bond with this ozone. So how many lone pair it is having? 1. So yes, it is an answer. So we have to tell lone pair of electron central atom should be 1. So yes, ozone has, the central atom has 1 lone pair. Yes, an answer. Water, central atom oxygen, we know it has 2 lone pair, recently drawn. So no. SF4, sulfur has how many electrons in its valence shell? So 6. 4 bond pair, 1 lone pair, obviously, but drawing also for you. So steric number 5, so 1 lone pair and 4 bond pair. Although shape is not asked, but I'm still writing because So you may also revise. So lone pair 1, yes. ClF3, it has 7. So okay, now I'm not drawing, we're just quickly moving to the shape. You can practice it. So ClF3, how many bond pair? 3. Chlorine has how many electrons in its valence shell? 7. So 7 minus 3 is 4. So how many lone pair? 2. So because it has 2 lone pair, so not an answer, because we have to tell 1 lone pair. NH3, obviously 3 bond pair, 1 lone pair, so yes, answer. BRF5, 5 bond pair and 1 lone pair, because bromine has 7 valence electron. 5 is used, so 2 electrons are remaining, so 1 lone pair. So yes, this is also an answer. XeF4, 4 bond pair. Xenon has 8 electrons in its valence shell. So 4 electrons will be remaining, so lone pair will be 2. So not an answer. So how many options we had? 1, 2, 3, 4. So we have 4. Moving ahead. The same logic you have to apply again and again. Linear shape molecule. Now I'm just discussing few, the rest you can do by yourself. XeF2, I guess you can bond pair 2. 6 electrons are left, so 6 electron as in 3 lone pair. So steric number is 5. So if I'm having steric number 5, lone pair will acquire which position? Equatorial position. So lone pair acquiring equatorial position. We have done it recently. So it will be a perfect linear shaped molecule, although steric number is 5, but this will be a linear shaped molecule. You are asked that how many species are linear, so yes, it will be linear. Talking about I3 plus, iodine has how many electrons in its valence shell? 7 plus, as in 1 gone. So how many left? 6. So 2 iodine are coming. So 2 are used. So how many lone pair I'm left with? 2 lone pair. This is I plus. So this is actually the Lewis structure of I3 plus. But draw its VSEPR structure, sir. It has 2 bond pair and it has got now 2 lone pair. So shape will be bent. Although shape is not asked out of us over here, but okay, shape is only asked. Okay, so shape is bent. So because this is a bent shape molecule, so not an answer for us. What carbon suboxide? We have done it in redox reaction. Doing it again. This is the geometry of carbon suboxide. Obviously, I can see because there are only steric number 2, 2, 2, 2, 2 for all. So carbon is linearly shaped. So yes, this molecule is linear. What about I3 minus? Sir, iodine getting 1 electron. So how much electron it will be having? 7 plus 1 is 8. So 8 electrons now this iodine has. How many bonds it is forming? 2. So 1 pair, because it will be having 8. So 1, 2, 3. So 3 pair of lone pair, 3 lone pair of electrons and 2 bond pair. And this is I minus because it has to acquire 1 minus charge, because question is telling us we have to draw the structure of a molecular ion, and it is I3 minus. Now, what can you comment about the steric number? Sir, bond pair is 2, lone pair is 3. So steric number is 5. Sir, 1, 2, 3, 4, 5, 6, 7, 8. Sir, this is again that case. Which case? Sir, lone pair will occupy equatorial position. So again, the shape will be just like lone pair will occupy equatorial position. So shape will be linear. So I3 minus is also a linear shaped molecule. Now, CO2, we already know it is linear. SO2, because of presence of lone pair, it will be bent. So not an answer. BCl2, linear. Boron has 3 electrons minus, so it will get 4 electrons. So boron having 4 electrons now. 1 Cl, 1 Cl, 2 electrons are lone pair. So it will also be, this is BCl2 minus. So this is also a bent shape molecule, so not an answer. So how many linear molecules I have? 1, 2, 3, 4, 5. Although I said I will not do this, but I'm doing such questions so that you may at least understand VSEPR theory is loved by JEE. Moving ahead. Now, next question says number of molecules ions having, okay, trigonal pyramidal shape. This is trigonal pyramidal, yes. Trigonal bipyramidal, as in steric number 5. Symmetrical case, no lone pair should be there. BRF5, sir, bond pair 5 but lone pair 1. So this will be square octahedron geometry, you will think. Square pyramidal. We are asked square trigonal bipyramidal, so not an answer. PCl5, yes sir, steric number 5, 5 bond pair, no lone pair. Now, this is I mean, in complexes also we'll see. I told you, no, they generally use inner shell. Generally, not always. Generally, the inner shell orbital is used for hybridization, and this is valid for complexes. So I'm telling you, its hybridization is dsp2, its shape is square planar. And you, although sir, if I do not know this also, it has 4 bond pair, and okay, then you'll get confused about the lone pair. So this is a coordination chemistry logic. So this is a square planar molecule, so not an answer for us. bf3 is trigonal planar, so not an answer for us. Now iron has, now it has got 5. Go by your steric number trick only. It has got 5. So because it has got 5, obviously this will also be a trigonal bipyramidal shaped molecule, although its hybridization will be dsp3, because as told you, d block complexes generally uses inner D shell for their hybridization. Not always, we'll be discussing them separately, but just by the basic which we have got till date, till now, because steric number, because bond pair is 5, so definitely it may acquire a square bipyramidal geometry, and it acquires also a square bipyramidal geometry. So how many molecules I have? 1, 2, 3. So my answer is 3. Moving ahead. Now again, the shape we have to discuss. I guess this is quite okay. This. Now, NCRT generally do not publicize it much, but P block NCRT does. In chemical bonding, NCRT do not discuss this, but in P block element it does, and this is my job to combine. So combining. So discussing about IF7, sir. Central atom is attaining 7 combining atoms. You said 6 will come. Question is not saying it is stable. It will definitely, actually in nature, in specific conditions also, it is not freely existing nature, but if at all you will try to form it, IF7 is the only molecule in which central atom is surrounded by 7 combining atom. So IF7, what will be its shape, sir? When we were having 6, what we did, 4 was in a plane, 1 up, 1 down. When we were having 5, what we did, 3 in a plane, 1 up, 1 down. When we have 7, 5 in a plane, 1 up, 1 down. So shape will be pentagonal bipyramidal. Shape will be 5 in a plane, 1 up, 1 down. So 5 in a plane will form a pentagonal plane. 1 and 2 bonds are axial. But obviously angle by mathematics also you can say, but this is a factual science, which is axial are obviously 90 degree, and that those equatorial are at an angle of 72 degree. But the repulsion which we know through trigonal bipyramidal, in trigonal bipyramidal, axial bonds were larger in magnitude. In square bipyramidal, as in octahedron, every bond length was similar, and here the equatorial bond length increases and axial bond length is slightly lesser. This is also a good logic, a P block logic, not valid for advanced, but still for those who want to walk an extra edge, telling. Now, one shape, after this one shape also you again should know. Sometimes what I have told you, central atom is surrounded by 6 atoms comfortably. When after coming of those 6 atoms, one lone pair is also introduced, then the octahedron breaks. So that shape is known as broken octahedron, or technically distorted octahedron. So how can you identify somebody's distorted? We cannot draw that shape. We are not supposed to draw that shape only. With the common sense only we can feel this, that if 6 combining atoms were there, they were forming a perfect crystal, perfect octahedron. Now if those 6 combining atoms are further disturbed by presence of lone pair, then the lone pair will have high repulsion, so it will break away the octahedron. So whenever you will throw someone outside the window, the person will definitely die. But what type of bones will be broken will be different in all cases. So that's why not drawing the shape, but just telling you broken or distorted octahedron. Now example, like XeF6, bond pair 6, but xenon has 8 electrons, so 1 lone pair will be left. So this is a case of 6 bond pair, 1 lone pair. Steric number is 7, but shape will be octahedron distorted. Tellurium, oxygen family, us se tipo, tellurium has 6 electrons in its valence shell. How many electrons it is gaining? 2. So 6 plus 2 becomes 8. So 6 bond pair and 1 lone pair. Again, this was actually asked by JEE Advanced only. So I've taken those examples from all the places and giving you in a precise. I have put on a lot of hard work, but this hard work will only be fruitful for us when you will revise this bonding very thoroughly. Moving ahead. Now, again, okay, first let us go to that question. Now we know this S is pentagonal bipyramidal. So S is 3, S is 3, no, S is 3, no, S is 3, no. So again, similar, I mean, it is in a Ziffy, I'm getting answer. For rest of the molecules, you can obviously attempt. Moving ahead, this I've already discussed. Now, one thing, okay, why I have included this question, I3 minus shape, we know what is shape of I3 minus. Shape of I3 minus is I3 minus we again recently drew na? Yeah, so it is linear. So S is 4. S is 4, no. S is 4, yes, maybe. S is 4, yes, maybe. S is 4. Now see, in JEE also you should do this. Just go by one which you are confident of, which you maybe remembering through practice, and you can clearly eliminate options. So left with 2 options only. Now S is 4, done. What is NO2 minus? NO2 minus and NO. I've intentionally, because I'm mixing atomic structure over here. What is NO? Shape of NO? I mean Lewis structure of NO. Sir, it's an odd electron species. Odd electron as in some unpaired electron will be there through atomic structure. We know if I have unpaired electron, I'll have a tendency to get attracted by external magnetic field, because I want to pair my unpaired electron, cancel my magnetic moment, so I'll be attracted. So because NO has odd electrons, so it will be having a paramagnetic nature, because getting attracted by external magnetic field is called paramagnetic nature. Discussed in atomic structure. In chemical bonding also, after MOT, this magnetic property is discussed, but because MOT I'll be discussing in bonding too. So telling you now only, because atomic structure we have discussed. So NO will be a paramagnetic species. So Q will be 1. So Q will be 1. So definitely Q is 1. Okay, Q is 1 here also. So again, I have to check. Now, what can you say about NO2 minus? Sir, this oxygen is getting 1 electron. So whatever unpaired odd electron the molecule was having as NO, all odd electron are removed. So this becomes a all paired electron, and all paired electrons are generally do not wish to get attracted by magnetic field and gets it actually repelled. So NO2 minus is a diamagnetic species. So R is 2. So R is 2, R is not 2. So B is your answer. The shape of SO2Cl2, you can easily see it is tetrahedral, because it will be having 4 bond pair and no lone pair, because oxygen will be requiring 2 bonds. Simple. Moving ahead. Now, I'll sip some water, and again a theoretical question. Quickly go through it. So I suppose you have got the answer, because this is a simple application of theory what we have learned, that is axial bonds are larger in size. So because axial bonds, the 2 axial bonds are larger in size, so they'll actually be weaker and broken easily. So it is saying it is stronger. So obviously this is incorrect, and C is your answer. Moving ahead, next question is asking you OF2 molecule. You have to tell about the OF2 molecule. So the number of lone pair on oxygen atom. So let us draw that OF2 molecule for us. Yes, definitely it will be having 2 lone pairs. So lone pair oxygen is 2. This is perfectly correct. Now, I'm leaving this second option, first dealing with other one. Oxidation state of oxygen is -2, sir. Through redox also, through periodic table also, we know fluorine is actually -1, and in presence of fluorine, oxygen has to acquire a positive oxidation state. So it will acquire oxidation state of +2. So this is wrong. Obviously, this molecule is a V-shaped molecule. This is right. And because it's a V-shaped molecule, so obviously it is not linear. Now, why I have left that one is because it is again an application of whatever dipole moment characteristic we have studied. I mean, just remember the structure of water molecule. Now, if you just see, when we have taken this water molecule, it is quite evident to you that when oxygen is bonding with hydrogen, what is the dipole moment telling you through the electronegativity? Sir, oxygen is electronegative, so this is minus and this is plus. So now, because this is minus, this is plus, so where will be the concentration of electrons be at large? large amount? Sir, because so this shared pair of electron will be more concentrated at oxygen. Here also these shared pair of electrons will be more concentrated at oxygen. Now just do like this. If you are the central atom, and to the shared pair of electron, if you have attracted those shared pair of electron, then your shoulders are heavy. So they'll be relatively far apart. Far apart with respect to whom? Let's say this value is theta. Let's say this theta is theta 1. Now here, because fluorine is more electronegative, so my shoulders has been relaxed because they have taken those electrons, and the electron density on my shoulders are less. So obviously I can relax my shoulders. So if I'm relaxing my shoulders, what can you suggest about the bond angle? Sir, this theta, let's say this is theta 2, this theta 2 will be lesser and this theta 1 will be larger. So this is just an application of the common sense of uh, central atom with respect to bond angle. I mean, if I am electronegative, my bond angle will be relatively higher, and if I am electropositive, then the electron density has been taken away from me. And if it has been taken away from me, then what is bond angle actually? It is the angle at which these bond pair of electrons are oriented, and it is always decided with respect to the central atom. So when I'm not electronegative, I can ease and relax my angles. So this theta 2 will be lesser. Although through theory we know for water molecule, we have discussed that also, the angle is definitely lesser than 109 degree 28 minute as per VSEPR theory, and it is 104.5 degree. So this, if this is 104.5, then this theta 2 will be lesser than 104.5. A beautiful thing that the question is asking you, that it is lesser than 104.5. So obviously this is also correct. So our correct options are 1 and 2. So 1, 2 and 4. Okay, 1, 2 and 4. So D becomes our answer. Moving ahead. Now, which of the following are isostructural? Let us draw their structures. Sulfate, sir, sulfate we have already drawn. So let us draw it again. Sulfur, double bond O, one O minus and one more O minus. So although I have drawn it in a 2D plane, we can now apply the VSEPR theory. So how many bond pair it has got? 4. How many lone pair? 0. So shape will be tetrahedral. Chromium, what is electronic configuration of chromium? 4s1 3d5. So outermost electrons are 6. So how many bonds? Because it is a d block element, so obviously it can expand it octet. So how many electrons it can form? 6. So chromium, CrO4 2 minus. So this is Cr, double bond O, double bond O. In the same way, this is O minus, this is O minus, because just like sulfur, chromium also has 6 electrons in its valence shell. So how many bond pair? 4. Lone pair 0. So this is also tetrahedral. So both are structure tetrahedral, so isostructural. Silicon, carbon family, so obviously this will be tetrahedral. Titanium, electronic configuration 3s2, 4s2 and 3d2. 4s2, the 20 till calcium, and then 3d2. So valence electrons are 4. So because it also has 4 valence electron forming 4 bonds, so no lone pair, so it will also be tetrahedral. So yes, they are also isostructural. Now ammonia, sir, it is trigonal pyramid. Nitrate ion, trigonal planar. I'm drawing this nitrate ion again for you, but I guess we have drawn it so many number of times. Coordinate bond will be replaced by this plus minus and then one more minus. So this is overall NO3 minus. It is trigonal because bond pair is 3. No lone pair on nitrogen. So this is trigonal planar. So this is planar and this is pyramidal, so not isostructural. BCl3 is trigonal planar. BrCl, okay, 3 bond pair and 4 electrons as in 2 lone pair. So steric number 5, lone pair will acquire the equatorial position, so it will be bent T shape. Bromine, 2 chlorines, 1 up, 1 down, and these lone pair. So this is bent T shape, this is trigonal planar, so not isostructural. Now what are my answer? 1 and 2. So yes, moving ahead. Okay, now a P block logic, a very important P block logic directly related to VSEPR theory. Now you should know this also, that actually what PCl5 do in practical nature is, PCl5 exists in nature because one molecule is existing, so there must be presence of other molecules also. So what two PCl5 do with each other, that two PCl5 molecules interchange ions. Why they do so? In solid state, when molecules approach each other, because they are it is PCl5 shape is trigonal bipyramidal, but when it is isolated, when molecules are isolated in gaseous state, but when PCl5 approach each other in solid state, molecules are quite close to each other, so they can interact with each other, they can react with each other. And what reaction, this is a factual thing also, what reaction actually takes place is, one PCl5 loses one chlorine and forms PCl4 plus, because chlorine is electronegative, can be removed as Cl minus, and that Cl minus is attained by the other PCl5 and it becomes PCl6 minus. So this phosphorus was having 5 electrons, lost one is having 4 and formed a tetrahedral cation. This phosphorus having 5 electrons received 1 Cl minus with extra electrons, so got 6 electrons and forming 6 bonds with now no lone pair, so will be an octahedral. And remember, tetrahedral and octahedral are more stable and symmetrical shapes in nature. So in solid state, it exists as a tetrahedral cation and a octahedral anion. So our answer will be A. But a very important famous fact of nitrogen family, telling you, when you talk about PBr5, so again in gaseous state it is what you know, which is trigonal bipyramidal, but in solid state, sir, this will also do the same thing. Yes, they will also interact. Yes, so this will lose, obviously bromine is larger in size, so it will definitely try to lose bromine and will form PBr4 plus. So the cation is same. Who will be the anion? Sir, PBr6 minus. But now bromine is much larger in size, because down the group size increases, that it increases drastically. So tetrahedral, octahedral molecule, remember I said when combining atoms are small, because bromine is so large, so at extreme condition you can form that PBr6 minus. But actually this PBr6 minus quickly gets broken into PBr5 and Br minus. So who are the cation and anion in case of PBr5? Cation is tetrahedral, but anion is simple Br minus, not PBr6 minus as in case of PCl6 minus. A very important fact you should keep it in mind, because JEE asked this, very probable for next exam. Now, the correct order of bond angle, sir, bond angle we do through spectroscopy. We know a VSEPR, so we do not have to do experiment. We do not have to learn the data. We can apply a logic. BF3 is, sir, it is trigonal planar. So bond angle will be 120. PF3, 3 bond pair, 2 lone pair. So steric number 5. Lone pair will acquire equatorial position. So lone pair equatorial position. Bent, and a straight fluorine. So what is this bond angle? Sir, it was 90 degree, but because of repulsion, it will be less than 90 degree. So I do not know what this angle is, but this theta is definitely lesser than 90 degree, because 3 bond pair. And okay. Phosphorus has 5 electrons. So 3 bond pair, 1 lone pair. I'm sorry. 1 lone pair. I'm sorry. Okay. So if we have drawn this, it will be true for ClF3, because ClF3 has 3 bond pair and 2 lone pair. So if we have drawn this, at least we can save some time. This is Cl. So for Cl it is right. For ClF3, angle is less than 90 degree. Now again, moving to the this is now going to PF3. Sir, this is 3 bond pair and 1 lone pair. So steric number is 4. So this is phosphorus, lone pair, 1 fluorine, 2nd fluorine and 3rd fluorine. I do not know what is this, but this is obviously lesser than tetrahedral angle. So you tell me, you have to tell me the increasing order. So who is having the lowest? Sir, now theta is less than 90 degree. So ClF3 will have the least, followed by PF3 less than 90 degree, and largest bond angle is of BF3 120 degree. Simple. VSEPR theory application. Moving ahead. Now Again, an application of again dipole moment. The question is telling you when because fluorine is more electronegative than nitrogen, then NF3 and NH3 dipole you have to compare. Now it is saying that the dipole moment of NF3 is greater. So I have drawn that picture for you to save time. Obviously, we know the shape is trigonal pyramidal. Because of lone pair, because this is nucleus and this is lone pair, so we know what is dipole, an electric vector, an electric field vector whose direction is from positive to negative. Nucleus is positive, lone pair is negative. So dipole moment because of the lone pair will be acting upside here also, here also. But now go to the electronegativity and dipole moment application. The triangle that has been formed by the pyramid of NH3, nitrogen and hydrogen, among them, who is electronegative? You tell me. Sir, nitrogen is electronegative. So this is delta negative and this is delta positive. So what will be the direction of vector from positive to negative? So it will be this way, from this side also, from this side also. Although it is a vector of from a triangle. So there will be some x component and there will be some y component. But the y component given by these NH3 will also be upside. So this mu and this mu will definitely get added and the mu net that you are going to get will be high as compared to, because in NF3 fluorine is electronegative than nitrogen, so it will attain a positive charge. So here the dipole moment vector because of the triangular NF3, trigonal pyramidal NF3 will be acting downside. So there in y-axis their vector addition will be acting downward. So this mu will be getting cancelled by the mu of lone pair. So here mu net will be obviously lesser because whose mu will be dominant? Sir, obviously of lone pair. So this lone pair is getting subtracted and this lone pair dipole is getting more, although this value will be much less in comparison to the vector of the lone pair, but still I'm adding to whatever the mu of lone pair is. So this will be more polar and this will be less polar. In the options, both the statements are given out to be opposite of what we have seen. So both statements are false in this case. A very beautiful question. Moving ahead. Now, again the same application. Sir, CCl4 is non-polar because tetrahedral. So this is non-polar. Ammonia, CH4 is also non-polar. So because, now see, C bond H is approximately of no electronegativity difference. This is a highly electronegative bond. C bond Cl individually is very polar. But because of vector addition and symmetrical structure, this will get cancelled. So dipole moment of both will be equal. Dipole moment of both will be equal. This is showing some I. Dipole moment, okay. Oh, only this option is telling you it is equal. Now let us compare with CHCl3. Although shape of CHCl3 is also tetrahedral, but here because all bonds are not same, so the vector addition will not get cancelled because one C bond H is not having the similar magnitude of charge as C bond Cl. So because these are dissimilar atoms, so this will definitely has some vector because over there vector addition will not be getting cancelled, so it will be definitely having some mu. So this is polar, so this is polar, so option C is right. Moving ahead. Number of non-polar. Okay, now again you have to tell me number of non-polar. So let's do, this is polar because linear HF is polar. Water is definitely polar, so not an answer. SO2 is a bent shape molecule, so some vector will be, mu will be there. Hydrogen is a non-polar. Hydrogen is simply a non-polar species, no dipole only. CO2, internally it has a dipole, but this vector and this vector will get cancelled out because it is a symmetrical shape molecule. So vector addition is 0, hence it is a non-polar, so an answer for us. Methane is non-polar, yes, symmetrical. Ammonia, no, there is some vector, in fact more polar than NF3, so not an answer, not non-polar. This is also polar, so not an answer. HCl is a polar molecule. Recently we have seen, although this is tetrahedral, but there will be some vector addition, so it will also be polar, so not an answer. BF3, although B bond F is polar, but overall shape will be trigonal planar, vector addition will cancel each other, so it will be non-polar. So non-polar, so an answer for us. So tick. So 1 tick, 2 tick, 3 tick. So how okay, 1, 2, 3 and this pink one, 4 tick. So answer is 4. Moving ahead. Now, we have to arrange in increasing order their ionic character. Let us go sir, ionic character. Again apply dipole moment. Sir, nitrogen is a non-polar, mu will be 0, so nitrogen will be lowest, lowest. So these two are probable candidates. These options are gone. Again, SO2 and ClF3, let us draw them. SO2 is S double bond O with a lone pair. ClF3 is 3 bond pair and 2 lone pair. So steric number 5. So Cl, 2 lone pair. See, this is asked so many times, right? This is fluorine and somewhat bent T shape of ClF3. Now, sir, if I have to compare them, go to the lone pair, because I know chlorine and fluorine, this is minus. So vector, this will create a vector on this side. This the lone pair will create a vector on this side. This vector and this vector will get cancelled. Over here also, these vector and the vector due to S bond O will get cancelled. But the vector due to lone pair is definitely of much higher magnitude. Lone pair repulsion is much higher than bond pair. So this vector is created by one lone pair. This vector is created by two lone pairs. So who will be relatively more polar? Which is having two lone pair. So relatively ClF3 will be more polar, and more polar will make this covalent molecule approaching ionic nature, because what is polarity of a covalent bond? Making it ionic. So ClF3 will be more polar, SO2 will be less polar. So ClF3 will be more polar. This is saying opposite, so this is wrong. So I've got my answer till here only. Now comparing still because I have got my answer, but still we are learning. So okay, now this is application of Fajan's rule. Because these are not covalent molecules. VSEPR theory is applied for covalent molecules. These are ionic molecules. So how use Fajan's rule? First we go to charge. Cations, okay, cations have same charge, but anions have different charges. Oxide has more charge. So more charge, more is the polarizability of an ion. If I'm getting more polarized, I'll be more covalent. So this is more covalent, so this will be less covalent, so more ionic. So LIF will be more ionic. LIF will be more ionic, this will be less ionic. Bingo. Moving ahead. Now, okay, again, that Fajan's rule application apply. We have to tell what is correct. Okay, so in first option, potassium common. Larger I minus is larger anion, so it will be more covalent. So it is saying less covalent, so this is wrong. This is saying more covalent, right? Do I have this option? Over here also it is saying okay. So I'm checking all the options by considering same option. So these are, we are asked which is correct. So obviously because this is wrong, so option 1 gone. But still I'm checking everything because we are learning. Now LIF and KF, sir, fluoride anion is common, so check the cation. Lithium charge is same, so small cation more covalent. So lithium will be more covalent. So this is right. This is right. Lithium is more covalent. This is right. Okay. So I guess option 2 both are right. So option 2 is definitely right. Now, tin anion is same. Look at the cation. The charge, more is the charge, more is the covalent nature. This is +4. This is +2. +4 is more covalent, more charge, more polarization. So this is correct. Next. D block cation, because of pseudo inert gas configuration, D block cation are more covalent, so this is also right. Then sodium S block cation, alkali metal, so CuCl, this is saying opposite, so this is wrong. This is also right. Okay, done. So option 3 is also right and option 5 is also right. So 2 3 5 2 3 5 2 3 5, option C, 2 3 5 2 3 5 are correct. Now moving ahead. Now, okay, this is an advanced question. Do not worry. Whatever we know, actually, I have included. I'm just given this question. We have already done these molecules. Now, this question is asking you to calculate the sum of lone pair on central atom. So, on central atom, you calculate lone pair. Okay, let us do it. Tellurium, Te, us say T-oxygen family, 6 electron, but there is 2 minus. So, this Te will be attaining those extra 2 electrons. How many bromine? 6. So 1, 2, 3, 4. I'm not making as VSEPR theory. Whatever it shape be, I'm calculating lone pair. So 6 it had, but it has got 2 electrons extra because this is overall 2 minus. So how many lone pair? All sir 6 have found bond pair. So how many lone pair it is having? 1. So 1 lone pair it is having. What about BRF2? BRF2 plus. Bromine has 7, 1 gone, so 6 remaining. So bromine is having 6 electrons in its valence shell. And 2 are forming bond with chlorine. Out of 6, why I'm saying 6? Because it is a plus molecule. So you have to lose 1 electron. So how many lone pair you have? You have 2 lone pairs. Simple. So this is 2. What is SNF3? We have done that also. SN, sir. Okay, nitrogen needs 3, sir. Then F3. Sir, sulfur has 6 electrons. All 6 have formed bond pair. I mean, bond pair you'll say 4, but pi bonds will not leave you with lone pair. So what is lone pair? 0. Okay, sir. 0. XeF3 minus. So xenon has 8 electrons. So xenon has 8 electrons. So 2 are shared by fluorine, but sir, there is one more fluorine. Sir, but after it, we obviously know that because there will be availability of empty d subshell, and xenon will attain a positive plus 2 electronic configuration. So 1F minus can also approach. So this F is approaching as F minus and coordinating its lone pair on empty orbital of xenon. But when coordinate bond is formed, a coordinate bond can always be replaced by a coordinate bond can always be replaced by a covalent bond. But if it is giving, it will attain a positive charge, but it was F minus, so plus minus becomes 0 and it will attain that extra minus. So ultimately what has happened is boron has 8 electron in its valence shell and received 1 more. So it becomes 9. So out of those 9, 3 has formed bond pair. So 9 minus 3 is left you with 6. So 6 electrons as in 3 lone pair. So it has 3 lone pair. So count the number of lone pair. This is 0. 1 plus 2 plus 3. So its answer is 6. So finishing this part of chemical bonding, and as you can clearly see, if you know your theory well, number of questions in for whole of your JEE syllabus for physical chemistry, for organic chemistry, for maths, for physics, I definitely say that you have to attempt more and more number of PYQs. But for inorganic chemistry, my friends, you can obviously see through the questions that we have discussed. If you know the theory well, if you have the theory in your tips, doing more number of questions is not going to help you that much, which revising theory and again will try to make you comfortable with the concept and logic, because it will be in your tips. So this is me, Gaurav Singh Arora, signing off with bonding 1. We'll be coming up with bonding 2. But I strongly suggest you revise this n number of time instead of getting more and attempting more and more questions. So revise this theory a lot of time. I also have gained some requests from some of my students that in YouTube some ad comes. So what I suggest is you go to the PW app and learn the lecture from our Elevate JEE crash course series, because when you go and read the lecture, maybe you can do and play it in a 2x speed if you are revising after listening it one time. So if you are revising, increase the speed by making it 2x. It will be much easier for you to revise all the concepts with obviously no ads. The lecture you can download obviously from there. So the description to which is given in the description section. So thank you. We'll meet in the next chemical bonding 2.